he asked if you have been able to download, if you want to follow along for IPython, if you have that Anaconda distribution or if you have IPython a different way. We'll put the link back up here in a second, but that's one of the things he mentioned. And I'd send out a link, but it might be like an email that's buried. But if you're on the Wi-Fi and you do a search and you do Anaconda and Python, you'll go to a website for Continuum Analytics, and they have what it is it's like they've encapsulated all of these Python libraries so that you can just install them all at once. So if you're interested in following along, that distribution includes IPython. So.
Awesome.
Here's your question.
Sure.
So I already have IPython 2.2, I think.
Okay.
I probably just got it by doing pip install.
You should be fine with 2.2.
Okay.
Make sure, if you're not using Anaconda, make sure that you have matplotlib
Okay.
and pandas installed.
Definitely have pandas.
Okay.
I'm pretty sure I have.
Okay. Yeah, I think, I don't know if it comes with it.
I
If
just,
it
I,
doesn't,
don't,
then.
I just don't want to hose my environment by trying to install over it. I don't know enough about how it organizes with the environment.
Yeah, so Anaconda does not play very nice with any kind of virtual environments, so you can't really just like spin up your own virtual environment and then try to go back and forth with it. So
probably uninstall.
yeah,
No, I'm just not going to tackle it.
just like don't tackle it now. See if it should work. All this stuff's pretty low level.
Yeah. All right.
Where's our Mac?
The adapter? I don't need it. I got the HDMI right here, so
okay.
I'm just gonna go ahead and project off of that. All right, let's see if we got something coming.
Send a projector that sometimes people will hit.
Send to both. Should be the right one here. It's got the HDMI, and yeah, they got all the adapters here in case we needed it. That's going in. No, that's going into aux. Let me try. There we go. That did it.
Oh, okay. And
I did it here at least. Let's try sending to both. Hey, okay. Opa.
all right, it's 9:03. Would you like to be videotaped, officially video recorded?
It's up to you. If you think for the purposes
For like
of
post-production, or like the videos posted and all that.
yeah, sure, no problem.
We had a person yesterday running it, but they may not be here today, so I'll just start it.
Okay.
But I'm gonna have to run.
And go upstairs and do your thing up there.
Well, I'll run downstairs just to make sure there's not like a lot of people. Today seems a little bit better. Then I'll run upstairs because I always just like curious to see how the split is.
Right.
Yesterday we had like data This is like pretty cool. So I was just, for the speaker's sake, I just like, hope that there's an audience out there. If not, I'll send it to you. All right.
Cool.
Go ahead.
All right. Good morning, guys. It's a surprising turnout for Sunday morning at 9 a.m. So I, number one, applaud you on your zeal and desire to learn more about not only Python, but also data analysis in general. And just in case you guys are making sure you're in the right room, we're going to be talking about IPython today. So if you need to clear out, head upstairs and go to the sessions up there because you picked the wrong spot, now's the time to do so. All right, cool. So a quick agenda of what we're going to be going through today. We're going to go through some prerequisites. John already talked about it. If you don't have Anacondas installed, is it Anaconda or Anacondas? I can't. It's just one. Yeah, one Anaconda. Okay. I keep thinking of that terrible sequel to the movie Anaconda, which was also a terrible movie. So just bad news all around. My doc's showing up here. Let's hide this guy. Oh, come on. And then we're going to talk about myself for a very, very brief amount of time because I'm not as important as IPython is. Then we're going to discuss IPython, talk about pandas and matplotlib very briefly. We're going to talk about the data set that we're going to be going through as part of this tutorial, and then we're just going to dive right in. So like I said, before we get into prerequisites, how many people here would say that they're new to Python in general? Okay, great. And then similar question, how many people here would they say they're completely new to IPython? All right. Alan's just giving the old. So prerequisites, Anaconda. I actually had the short URL to be Anacondas because Anaconda was taken, but j.mp/anacondas. Go ahead and download it now if you haven't. We already have, so we should be good to go. Quick thing about me, there's me and my wife up there. I'm a solutions engineer at DataZoo. We build advertising technology. We're actually a machine learning platform that takes in all the data that we have about a user and then is able to serve them a relevant, contextual, and targeted ad. So the entire machine learning team and optimization team at DataZoo uses Python, IPython notebooks to convey information, show visualizations across the entire organization. I'm also a grad student at Tufts University, and I've been dabbling in Python for about 2 years. And Python is one of those amazing languages where you can just keep spending a lot of time with it, and really cool things start happening, especially as you follow tutorials that are available on the web or read through all of the books. So I would highly recommend, as you continue to discover Python, don't get discouraged, just keep trying it, run weekend projects with it, use IPython, use Flask to throw up some quick websites. It's really interesting and really fun. So talking about IPython is essentially an interactive command shell. It kind of exists on, not really on top of, but it's a replacement to the normal Python interpreter that you would use. It's really performant. It's actually often used for parallel computing, but the most important part about IPython, at least for this discussion, is going to be the notebooks. So those of you who are familiar with using tools like MATLAB or Maple are kind of familiar with the notebook idea, the idea where you can sort of stack different code segments and then run them to the point where you're able to get some really interesting data and insights in a really easy to use and visual manner. With regards to pandas, so pandas is a data analysis and data management tool set. So instead of using normal Python standard input-output tools to read CSVs or even plug into databases, pandas actually creates MATLAB-like data frames that you can then play with and add things into. It's also really fast compared to some of the other operations that you could run. With regards to matplotlib, it's actually just a plotting library. Also, once again, very similar to MATLAB. You'll see a lot of commonalities between MATLAB and Python data analysis because a lot of people doing that happen to exist in the same circles. You can do a lot of 2D and 3D plots. There's also, you can use SVG map data, so you can do something like tracking disease flows and epidemics over regions, for example. And there's also heat maps, and I highlighted heat maps in red here because part of the project that we're going to be working on today is going to be a heat map. Also, if anybody has any questions, feel free to raise your hand and interrupt. We'll consider this as a really interactive session. So here's the data set we're going to be looking at. We're going to be looking at the MBTA's late night tea data set. That short link right there is going to take you right to the CSV that we're going to be looking at. You can also just search for late night tea on GitHub, and you'll be able to find the data set there. It was introduced this past June, and as part of this contest that they're doing to get some really cool interactive data analysis or data tools that they could then develop into something as part of their new upcoming MBTA APIs. So the set that we're going to be looking at is going to contain ridership data across all the normal T lines, red, blue, orange, silver, and green, as well as a variety of the bus lines that happen to have MBTA late night service. And here's what we're going to do with it. We're actually going to use just IPython to build out a visualization just like this, where we're going to be showing the ridership across multiple lines in multiple colors. We just have enough room for the red line over here. Over from 10 p.m. all the way over to 2 a.m. with the stops lined out over here. Everybody good? Ready to go? All right, people are into it. Okay, so the first step that we're going to do is, assuming we've already installed anacondas and everything, we're going to open up our command line. And all we're going to type in is IPython notebook. And our notebook should show up. And it's going to show up in wherever your home directory is. So if you wanted to put your notebook into another directory, you can obviously browse to it this way. I'm just going to put it right here in my home directory. So we've got our IPython notebook here. As you can see on the top bar, these are your normal file input outputs. You can do very similar like a word processor. You can do all your copy and pasting, see it easily. You can also change the value of this cell here, so you could make it either just a code segment, or you could use Markdown to make it text, or you can just add raw headings in there too. What makes this really handy and really useful is that once you're done writing everything out, you can export it as an HTML and then ship it or upload it somewhere so that someone can easily see it and you can share your cool insights and visualizations with everybody. So has anyone having trouble getting to the IPython notebook view right here? It's just IPython notebook right there. You should be able to run the same command in Windows from the command line. Does it not work? Have you installed Anaconda? Okay, it's working? All right, cool. So you've got your notebook ready to go. So the first thing that you want to do is you want to get all of the relevant Python modules imported. Like we talked before, we're going to be using pandas and matplotlib here. So I'm going to go ahead and import pandas as PD. And then I'm also going to import the, from matplotlib, I'm going to import pyplot, which is the Python plotting engine. So I'm going to do import matplotlib.pyplot as PLT. Sure. Are you going to post the syntax? The entire thing, I'm going to post it up, yeah, when it's done, so you guys can walk through it. You can also, we're also going to be using the date module as part of matplotlib. I don't know if I actually ended up using it in the final visualization, but why not, you know, as mdates. And we're also going to import NumPy, although I don't think I use NumPy at all, but I have a go-to set of imports that I do. I just copy and paste it off of like a text file that I have, and these are part of it. And rather than running into a roadblock where we end up not using, or using NumPy but not having it, we're just going to go ahead and use it just in case. So,
is your keyboard shortcut for running?
For what?
For running the code?
I don't know if there's there probably is, but Shift Enter, there you go. See? Wisdom of the crowd coming in. I just usually hit play because it's really cool and I feel like I'm doing something with my life. So the first thing, if you guys haven't downloaded the MBTA data file that I talked about before, once again, here is the URL, j.mp/late night MBTA data. It's a big CSV file, so it might take a little bit of time to download, but go ahead and do so. And keep that in the same directory as where you opened your IPython notebook. You can also browse to a folder within IPython and get it out, but for simplicity's sake, we'll just keep it in the same directory. So I'm going to go ahead and call it my tdata file. And it's going to be open, and it's called late night through 7 June 2014.csv. And then tcsv equals pd.readcsv tdata file. Converters equal, and I'll explain this once we're there. You know what? Let's save ourselves some time. Let's copy paste it. So that converters parameter in here, what we're doing actually is we're taking the scheduled date column within the CSV. So if I opened up the CSV itself, you'll see scheduled date right here. It's actually in a date format in Excel, but Python doesn't know that. Pandas doesn't know that. So we're actually saying that we're going to use mdates, which is that matplotlib dates module, and we're going to strip the date out of that text, and we're going to use this format where it's the month, the day, and the year. Yeah?
What was the URL to the data set again?
Yep, it's j.mp/late night MBTA data. Yeah. So there should be a link in there. So if I go to it, it's going to open it up in GitHub, and you can actually hit view the full file. And I think you just copy the link as, you'll be able to get it. And I also just realized that because we're in my home directory, that tdata file isn't there. So I'm going to quickly move it there. Okay, that should be there now. All right, so if all goes well, if I hit play, it should be able to load the data and change this or create this TCSV for us, which will be our data frame. And it's thinking. That little star there in IPython means it's thinking. So give it a second. Looks like it did it. Now, to validate that I have the data frame installed or inputted rather, I'm just going to type in TCSV, hit play, and there it is. So you've got our schedule date right here, and it's converted the date into a numeric format. We've also got our late night route, our line, our route station, et cetera, et cetera. And just for your notification, if you guys are still playing around with Python and just want to mess around with IPython for a while, you can do everything you would normally do in Python right here. So you could print whatever you wanted. And the handy thing about this is that instead of trying to go back and retype commands, you can go back and edit it and have fun with that. All right, so the next part of this is actually going to be dealing with a little bit of a workaround that I had. So remember from when we were looking at our data set here, we've got the names of all of the MBTA stations here on the left. It's kind of scrunched in with the resolution of these projectors, but we'll work with it. These names actually aren't available within that CSV, at least in the format that they are over here. So what we're actually going to do is we're going to create an array that is all of the names of the red line T stations or the blue line T stations or the orange line or all of the above, and use that array to create the column name, or rather the row names for our visualization. So instead of having you guys type all this out, what I'm going to do is put this up on Pastebin, and then you guys can just copy and paste it into your own notebooks. So paste this there. Yeah. A comment to this URL, the Pastebin URL, or? Oh, yeah. Yeah, I'll actually put it right into the notebook so we can keep it there. Let's see here. Oops, move this guy up. Let's make this a heading. Ooh. It's like magic. I love IPython. All right, so here's our Pastebin. That may be a little too complicated, but you guys can figure it out. VA3, GVV82. I'm also going to paste that right into this view here that we're all seeing. Let's call this column headers. There. So what we're going to paste, let's just go ahead and put that here. As you can see, we've got our red line stations, blue line stations, green line stations, and orange line stations here. Fun little anecdote here. I changed the order around by mistake on one of those stations, and it made it end up looking like a lot of people were going to Fields Corner Station, and I was very confused as to why people were going to Fields Corner at 3 in the morning, and it was a very strange moment for me because I couldn't figure out until I went back to my array here and realized that I put it in the wrong spot. All right. So the next step that we're going to do, I'm going to hit play here to get those arrays created, is we're actually going to trim our data frame to look at only the MBTA lines, the subway lines rather. So this command right here is basically saying that we are going to take our data frame and we're going to filter it and say that, all right, we're going to filter it so that the line is one of these 4 lines, red, blue, green, or orange, because I don't care about the silver line. Sorry, those of you who came off the silver line, you're living too far away. All right, so everyone kind of following along so far? Getting there? Oh, this is getting out of the way here. Let's keep this up. Let's see, what's the best way for me to keep this data up here? Oh, I have an idea. And let's keep this afloat. Can I do that? Nope, maybe I'll try to just text edit. There we go. All right, so now this is going to stick up in the corner of the screen here, so you can always have that. And I'll keep adding things I can copy and paste over here. Yeah, so to get to the notebook? So all you have to do is open up your command line and type in IPython space notebook, and it'll open up for you. Make sure that you take your data set and you put it right in the same folder as your notebook. All right, let's keep moving things right along here. So we're going to go ahead and create our new data frame called trains only with just the lines of service that we're going to be looking at. Just to validate, I'm going to look at trains only right here. And there we go. We've got our scheduled date, the late night route 1. There also be late night route 1, our line, our station, day of week, the hour, and then the TRX 15 minutes means the in which 15-minute increment did the transaction happen, whether it be 0, which is right at, looks like 10 o'clock, or within the 10:15 to 10:30 window, or 10:30 to 10:45, or 10:45 to 11. So let's scroll our way down. Now what we're going to do is we're going to take all of this data and we're going to perform a group by so that we can group all of the data by the hour, by station, and by line. So that means that we're going to get in our resulting data frame a statement of just all of the lines per hour as opposed to per these 15-minute increments and the number of transactions per hour in those lines. So I'm going to go ahead and put in my group statement down here. Actually, let's put it right here where we don't need this anymore. We're going to call the new grouped by data frame grouped, G-R-O-U-P-E-D, equals trains only dot group by. Do you guys want me to boost up the font size here? There we go. Dot is in. Nope, that's the wrong one. Sorry. There it is. So grouping by line, route station, and transaction hour. And as index is going to equal to false. So let me explain this. And missing my closing bracket here. So, as I said before, we're grouping by line, by the station, and by hour. The as index field here means that none of those fields that we're using or that group we're grouping against is going to be considered the index. Usually when you have an index, you want to put in something that is just a unique variable or unique identifier for that index. Oftentimes it would be something like the transaction ID if you're looking at, let's say, in-store transactions or financial transactions. But we don't have to worry about that. Our data frame is pretty small. We're not going to be referencing anything by a unique index value. That's why I have as underscore index equals false. So hit play. Oh. And then if I look at grouped this time, oh, my mistake. It actually creates a group by object. I'm sorry about that. I need to take the group by object and reconvert it into data frames. So in order to do that, we'll just do that for one data frame. We'll start with the red line. So red line equals grouped, route station, dot is in, red line stations. Oh, thank you. If you didn't tell me it, then the system would have, and that would be even more embarrassing. Oh, there I go. What did I do? Is in. Oh, something happened here. What did I do? Grouped equals transform group by as index equals false. It should be working. All right, let me just try copy and pasting directly from what I had. Is it different there? Oh, that's right. The thing that I forgot to add at the end of my group by statement here is transactions.sum. So what it was actually doing is it was keeping the group by, but it didn't know what to do with everything we were grouping. So what we wanted to do is group it so that we sum all of the transactions. So that entire line looks like this. Group by equals trains only dot group by, line, route station, TRX hour, and then you have the transactions.sum. So you're actually grouping by transactions and summing them together. That should solve our problem with that not being a data frame. So if I go into grouped, I'll see it there. And here we have everything grouped by line, route station, hour, and we summed the transactions for all of those. Once again, really good way to just take a look into your data as you're making changes and making modifications.
So is that just figuring out each unique combination of line, route station, and hour?
No, so what it's doing actually, it's taking, oh Oh, yes. So yes, it's taking those three combinations and grouping the transactions together. So what we're doing is actually we're not looking at dates anymore. So we're completely kicking dates out the window, and we're just going to be looking at all transactions that we've seen within the MBTA data set. And these transactions are normally split out by day, but since we're ignoring days, we're actually summing all the transactions together. And that's one of the handy things about using something like an IPython notebook as you're continuing to work on your various Python tasks, because you can keep track of all your variables, keep track of all your data frames, and look at them interactively. You could do the same thing within the command line or within the IPython command suite, but it's just so much easier to be able to scroll up and actually rerun code or re-execute something. So even when I'm not doing any kind of data science or data analysis or visualization, I tend to use an IPython notebook just because it's just a really easy way and intuitive way for me to go up and back and forth and up and down. So let's take just the red line here. In fact, what I'll do is I'll take all of these stations and put them into a new paste bin so you guys can use that. I'm trying to save you a lot of time typing here. And this would, yes. Oh God, too big. Well, we don't need the top bar anyway. Let's make this 24. There we go. And this would be individual lines grouped. All right. Next up, we're going to be digging back to the recesses of our brain and pull up some old-fashioned linear algebra. So those of you who forgot what matrices were or don't remember how to use matrices or really hate matrices, you can now walk out because we're only doing a little bit of matrix work. It's actually going to be really simple. We're only going to be pivoting, so it's not terrible. Okay, let's change this thing before I do that. So for the red line specifically, what we're going to be doing is that we're going to pivot the data so that each unique combination of station and hour has a value for the number of transactions. So I'm going to say, taking our red line data frame, redline.pivot, we're going to use route station actually this time as our index. That's where route station is going to be ending up here. So we're actually going to take the station and hour and use the station itself as the index in our data frame. We're going to set the columns to our transaction hour, and we're going to set the values to our transactions. So what does that give us in the end? An invalid syntax error because I can't type. There it is. Thank you. Nope, what am I missing? One more. See, Sunday morning, guys. So if I look at RF now, that's not right. What is happening? Okay. Oh, run this. Oh, I had a keyboard shortcut there. There. So now we have a 2x2 matrix where we have our rows being the individual station names and our hour being the actual hour of the transaction, and we have our transactions. So we are one step closer to that end state visualization where we have station names on the left and, on the rows and the hours for the columns. So things are looking up for us here. One thing you might notice, however, is that because we re-indexed everything, all of these station names are in alphabetical order. So when we actually end up pulling our visualization out, we'll still get the same data that we need. Park Street still has the vast majority of attendance, or rather transactions, but it's not going to look like this. It's not going to look like the actual progression of the MBTA subway line. Well, what we did earlier, when we made that array of red line stations, we actually established the order of each of those stations because we have Alewife all the way going to either Ashpond or Mattapan. So what we're going to do is we're going to re-index this based off of the array that we created earlier. So I'm going to say my red line data frame equals, this is a new data frame. So RDF is different from what we did before with RF. Dot reindex, index equals red line stations. Now one thing I will say is that I was not very good at naming my variables, so I immediately apologize for that. I realize when you have a variable named RF and RDF, and they're not very descriptive. So we've made that reindex. We're going to look at RDF now. And here we go. We've got our station names in the appropriate order that we want to, and we've got our hours going from 10 o'clock all the way down to 2 a.m. So yes, in the case of the MBTA data set, they did not reset 24-hour time into the next day. They just added another integer on top of it. So this is actually 1 a.m. and this is actually 2 a.m. and we'll reflect that in the actual visualization that we end up putting together. So we've established our set of data frames. We've created this new array that's going to actually end up being the source of our visualization. What I'm going to do now is I'm actually going to give you guys the commands to take not only the blue line stations, but also, or sorry, the red line stations, but also the blue lines and green lines and orange lines. And that's here. We're going to call this the reindex. And I'm just going to paste the pivot in there as well, so you guys can have that. There's the reindex, and before that, you got to pivot them. And you can run both of those in the same block. It shouldn't be an issue. So there's this, and submit. There we go. Kapow. All right, so we've got our stations grouped here. I'm going to go ahead and just group everything that we worked for. We did that. Repivot everything for all 4 stations. And also reindex for all 4 stations. And this should not be here. Let's get rid of this guy. Just run again, group, index. That's already, that did it already. And now we're going to start working on the plot itself. So in order to generate this plot, what we're going to do is we're going to iterate through an array or a sequence of all of the data frames that we're working with. So the first thing we're going to do is define that array. So all of our data frames are RDF, BDF, GDF, or ODF for red line, blue line, green line, and orange line. We're also going to set titles for each of those, and we're actually going to use just another array called titles for that. And we're going to call it red line, blue line, green line, loin. Ugh. We don't want a case of green loins, and orange line. Next, we're going to set the colors for each of the individual lines, and we're actually going to use that as a color array. So what we're doing here is we're basically saying that each entry in the array, so array position 0 is going to be the position for the red line. It uses this data frame, uses these titles, which is the red line, and we're also going to use colors. So we're going to say colors equals plt.cm.reds. I could go into a deep discussion as to what all of these mean, but essentially these are shades of red that are provided by matplotlib. So they're really handy for when you're building something like a heat map and you don't want to actually define the colors yourself. You can use these built-in colors. Similarly, we'll go into blues, plt.cm.blues, plt.cm.greens, and finally plt.cm.oranges. So we've got our colors array. Oh, PLT, sorry. So run that, and BDF is missing because I didn't define the blue line data frame above, because I didn't do this one, I guess. There we go. So that's one other thing too, is that sometimes when you get something like a variable missing or a value missing, that means that you didn't actually define it, and you can just go back up to that code segment, hit run, it'll put it into memory. If you get to a point where you feel like you need to back out and restart everything, you can actually interrupt and restart the kernel from here, and that'll flush everything out until you can run it back up from the beginning. It's really useful if you're dealing with really, really big data sets and you don't want to manage them anymore, and you just want to start from fresh. All right, so we've got our array of data frames, array of titles, and array of colors. One of the things that we actually want to do now is, for our plot specifically, append the row labels and the column labels. So as you guys can probably guess, we haven't put in the 10 p.m. to 2 a.m. The 10 p.m. to 2 p.m. column headings now. We're going to do that right now. So we're going to say, for each frame in our array of data frames, we're going to append our row labels. Row labels dot append frame dot index. So what this is doing is that we are going to go, and for each of the row labels for each of these data frames, our red line, blue line, green line, or orange line, we're going to use the index, which were the actual station names, as our row labels. That's where this append comes into handy. It's going to do that for each of the lines because we're iterating through in this for loop here. Next, we're going to add our column labels, and because we haven't defined them before, we're actually going to define them right into the statement here. So column labels.append, and we're going to create our array. 10 p.m., 11 p.m., 12 a.m., 1 a.m., and 2 a.m. Brackets are closed, everything's good. And we're also going to, oh, hold up one second. One step that I forgot to tell you guys about. So we actually haven't defined row labels and column labels. So if you tried to run this right now, it would say, I don't know what to do because I don't even know what row labels and column labels are. For now, we're just going to say that row labels are a blank array. Column labels are a blank array. And we have another array that we're going to be calling data. And that will become more evident when we actually get to the plotting library that we're using. So on that, I'm also going to add data.append frame as matrix. And what we're doing here is that we're actually taking that data frame and appending it as our data, and it's actually going to interpret it as the matrix because it is a matrix. So, doop, doop. All right, now we start getting into plotting. So we're going to start, whenever you define a matplotlib plot, you're going to start by defining the figure, and then you're going to define the axes as well. It's generally what it's doing is creating your canvas, your drawing canvas, which is your figure object, and then the axes help you define things like what the axes look like and what the actual visualization is going to be rendering on your plot right there. So that's easy enough. Fig, comma, ax equals plot dot subplots. Number of rows in our plot equals the length of our data frames, and because our data frames array here, which is 4, so we actually have four plots coming into here, into this one figure object. And what we're going to say for now is that they don't share the same x-axis. Now, technically, if we were to look at the end state visualization, they do share the x-axis, but for the sake of clarity, I'm actually going to say they don't, so that at the bottom of every single one of our 4 plots, it'll say 10 p.m., 11 p.m., 12 a.m., and 1 a.m. It's one of those things where if you had to scroll all the way down to get what time it was, it'd be too much scrolling back and forth. So that's why we're not going to be sharing the x-axis here. False. Unexpected end of 5. Did I kept this guy hanging? So what you're doing actually is that when you're defining both the figure and the axes, and it's going to be defining them both because when this plot, that subplot, so not subplot, it's going to actually fill in those 2 variables because the output or the return of this is 2 different variables that we set as figure AX.
I think there's a typo. The length should be so close brace of left. Yeah.
See, why can't I have you guys all the time? That'd be great for code review.
You can do only that.
Yeah.
You cannot write the code.
So where did you say it was? The len was. Oh, here we go. Yep. Thank you. And then this needs another one. Yeah.
You have 2 right traces.
Yep. Need to match this guy up with something. Well, is this gonna work? Let's see if that works. Nope. Messed it up. Axis subblock. X. That's not right. Oh, you know what? Let's just paste that from my working file, and we'll go from there. What's different about what we pasted? Oh, n rows, not n row. Yeah, and the share x is different. It needs to be a capital X. Case sensitivity, biting me in the bum again. All right. So what we're going to do next is we're going to set our figure width and height, as well as define it so that there is no frame around the figure. We don't want the border around it. So those are 3 simple commands. We've got fig.frameOn equals false, fig.set underscore fig height 30, fig.set fig width 15. Now these resolutions ended up working okay, or these heights and widths ended up working okay for my screen here locally, which is a MacBook Pro with the Retina display. So what that means is that sometimes it might appear blown up on your screens for other resolutions, just because Apple likes to create really dense pixels into one spot, and it looks really bad when you load it up on an external display or another monitor. But we'll see how it comes out. So we set those. And now what we're going to do is we're going to set our X ticks, which is the actual tick markers inside of our plots, as well as our Y ticks, and we're going to set the labels for all of those. Now, this is a lot of stuff for us to plot, so we're actually going to use a cheat code here. Going to give you a paste bin. You guys are going to paste it right into it, and you'll be able to see it, and we'll actually walk through it and explain it. as opposed to having you guys type everything. So I'm going to do this guy and give you guys another thing to paste bin on. All right, so made you guys a promise. I'm gonna go ahead and paste that here. Okay, so let's talk through and explain what's going on here in this jumble of code. As you guys continue to go through, you'll be able to see it yourself and play with it and edit it as you see fit. I'm doing this because we only have 10 minutes left and I want to leave some time for questions. So we've got our xticks here, which are just basically what our tick markers are going to be and where we're actually going to be placing the locations of the 10 a.m., 11 a.m., or sorry, 10 p.m., 11 p.m., midnight. We're actually going to keep this in the middle of the shape. So if you look back at the visualization, as you can see, the actual column marker is in the middle of this one shape for Alewife. Otherwise, you'd have it end up either on the left side or on the right side or somewhere else in between. Matplotlib is very particular about that kind of stuff. We're also going to do the same thing for the Y ticks, and they're going to be showing up right in the middle of our rows as opposed to on the top line or on the bottom line. We're also going to set our title as the title. I'm going to use this font here, this serif font, Adobe Garmin Pro. If you guys don't have this font on your system, you can change it to Arial, or if you're feeling really pluckish and annoying, you can change it to Comic Sans. But I wouldn't recommend it. I don't think anyone should. Next, we're going to set our whether the plot is adjustable or not. We're going to say that it's a forced box plot, so we're going to set using set adjustable. And we're going to set our tick labels here. So if we remember, we created that array of column labels earlier. So we're going to use that right here as our tick labels. We're going to say that their font size is 15, their font name is Adobe Garmin Pro. Set our Y tick labels. And then all of this stuff, setting your spine, iterative values, that's whether or not you want to show the actual row spines throughout. We're not going to be showing those. And we're going to say that we're going to hide the major and the major ticks for both the X and the Y axis, so we won't have lines jutting out from the edges indicating our tick marks. And then we're going to plot the legend. There actually is no legend here, but I have that in there as a standard paste. We're going to say it's a tight layout. What Matplotlib does by default is it adds a lot of extra space to your plots. So we're actually going to say that, you know what, truncate extra space. We want to have a nice tight layout. And then we're going to say that we're going to auto-scale our plot. And we're going to save the figure as a PNG file right into the same folder. So hopefully all this will work when I hit run. Uh-oh, what did it do? That's not a good sign. Use label, no label object. Okay, failed back to active renderer. All right, there's something in here that I put in as a way to cheat out of this because I've had this happen before. We set that. Okay. That would do it. So we committed a cardinal sin here, I would say, in that we went through this entire process and we actually never defined what that plot is going to be. We just told it, hey, make a plot, whatever plot you want, which the system went, I don't know what to do with this. So we have to actually define the name of that plot. I scrolled over it by mistake. We're just going to paste this here. So what we're saying is that we're going to change each of these plots to be a type of this P color type. This is actually one of the built-in heat maps in Matplotlib. The colors will be the color relative to the position in that array. So we had those reds, blues, oranges, and greens. And we're going to set the label as banana. This, I never figured out where this label came into play before, but if I didn't define it, it broke. So I just called it banana for now. You guys can use whatever you want. Put your own personal spin on it. And here, I'll add this to our last paste. I wonder if I can edit my own paste bins. I should be able to. So when I told you it was my last paste, I lied. What was the line from Commando? Remember when I said would I kill you last? I lied. All right, here's the new one. There's the final paste. So bring this back up here. Hide you a little bit more. There we go. Da-doop. Da-doop. Syncing, or is it just skipping? All right, so when you have a situation like this where things just aren't showing up, best bet, restart the kernel. The old IT strategy, have you tried turning it on and off again? And we're going to start fresh from the top. So, now, as you know, I'm breezing through this quickly. One thing that's handy about IPython actually is that if you do end up doing that, it'll still execute things sequentially. So you won't actually end up overriding something or starting a command and doing it before the previous command is finished. So that's really handy. There's also a run all command, but for the sake of completion, we'll just go through like this. Doot, 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 doot. Oh no. Failed going back to aggregate renderer. Is everyone else getting this error too? The aggregate rendering error? I'm willing to bet that I messed something up before. So
I think that was a bug report in IPython notebook, and I remember this.
you know what? Let's try this.
Yeah, like do the external like OSX or whatever.
So what we're going to do, and what I should have done earlier, is that I did not tell Matplotlib to actually render the plots inline. So that's what it's doing now. So let's see if that works. Chunk, 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 chunk. Oh, God. That is not what we want, though.
Try setting it to like one of the external, like you can say Matplotlib OSX.
Yeah, let's see. Live demo. All right, you know what? We only have 3 minutes left. Let's bring out the one that I know works from previous experience. And this is the one that I'll share online too, so you guys can actually use it. And it has little bits of information between each of those, so you guys can take advantage of that. Oh no, did I already mess this up? No, that's not right. There we go. So there's something that I was missing when we were typing it through, but when you guys see it, you'll be able to find it. What it should look like in the end, and I'm sorry we didn't get as far as to get this, but it should look like this, where you have your red line, your blue line, your green line, and your orange line all together in this handy visualization. I'm bummed that we didn't actually get to do it ourselves, but that's part of the process here, is just discovery and iteration and checking your own mistakes. Any questions that I can answer about IPython, Matplotlib, what we did here before we wrap it up and move on to the next session? Yep, I will share this. Actually, what I'll do here is you guys can write this down in your notebook. I will share this all as, I'll share the slide deck, and then I'll put this in the slide deck. And the slide deck will be shared as in fact, we'll use this as audience participation. What should we name our bit.ly here?
If you call it Datacon, your last name, it will be consistent with mine.
Great. Datacon Mullick, here we go. So the presentation will be there, and once I close up here, I'll actually add a link. J.MP, Datacon, M-A-L-E-K. And that'll be consistent with Alan's presentation coming up, J.MP/Datacon Downey. And I'll just add it as a closing slide here into this Google slide presentation. And I have to share this presentation actually with anyone with a link. Yep, doing that. So any other questions while this is going through? Right. So I used to be the type of person that like ended up using those JavaScript libraries for building your own slide presentations and deck and things like that. I didn't actually try the IPython variant of that. You could try it, give it a shot, but as far as my interaction with IPython, it's been keeping that same notebook view and just playing around with it and having fun with it. Public on the web. All right, well, if you guys have any more questions during the breaks, you can come up and ask me, but we're going to stop right here at 10 and move on to the next session. Once again, my name's Imran Malik, and thanks a lot, guys. Refresh. Thank you. For the data, so
Aaron came down and
oh yeah, so we're actually
Aaron
going
came
to
down and turned it on.
okay.
What
we made.
Okay.
We're gonna put that
I don't know. That's right. Because like I've been streaming, but the connection has been like so slow that it just has not been working out.
Let me see what it's recording.
Okay, perfect.
Okay. So, well, that's fine. I mean, all right. I'm trying to multitask once. So it's just not working as smooth as it was yesterday for whatever reason. Okay. We'll figure something out. You know, this is kind of a good start
as
to
long as the, I mean, that's what I was worried about, is that as long as it's being recorded, we're good.
Yeah. And we have the video here. I'm also recording, although I chose to do more of like a speaker. All right, so let's see here. We need the wireless. But this is a good kind of first step towards getting everything live streamed. We'll have to like get the next step. You know, the next Python meetup or the next.
It'll be like, yeah, use a wired cable and stuff like that.
I get everything. Yeah, it is. You know, and I was talking to Kevin yesterday a little bit more, and he was showing me some other equipment that we could buy, like to stream things for like $300, buy the hardware and stuff like that. So if we need to do something like that for. All right. So it should be functional. Yeah,
oh, this is not a percent.
Please work. Oh, hello. If I put it in a tiny irk. I can spell it right.
Yeah, that's very strange.
You know, the Wi-Fi surprisingly was somewhat sluggish yesterday, and I was not.
Okay, give me just 1 second. Let me put this thing up on public share.
Oh, it's all one.
Oh,
It's all part. It's just
okay.
like the Friday one. It's
Okay.
if you were you hear Friday or it's like a repeated one Friday, which is like just all. Yeah, I should have repeated that, but it's all just one big 3-hour block.
Is it, you guys go over like the scripting?
A little bit of scripting, and we approach it from a statistical point of view versus a. We're going to do some time of programming with R. This is more like intro to R and then some basic graphs and stats a little bit. But the scripting, I do more like. Here's a data structure type, a data frame, just so people can kind of understand, just like
If you look at that slide deck,
how to get started. So it's more important.
the first slide is what we call overview, and that's where the iPython.
Yeah, I wish we had faster speed. And let me get my.
Thank you.
And we'll have to get the display going too. Let's get that.
Really?
Okay, that's not an active plug, is it? Maybe
So
we might need to use his. If
it doesn't do anything. It says it's huge. You've already created one.
I'll get him up and then.
You have 2 notebooks running at the same time? Nothing in there called check, so yeah. This might be a window. So if you go over here, okay, so what might be happening is that you might not have permissions to write to this directory. You want me to show you how to project on that? Yeah. Yeah.
Jack, let me swap those.
Yes.
This is actually John's.
And you have
We weren't able to get it working for him. Disconnect here.
Why don't we actually introduce ourselves formally? Imran.
Good to meet you.
Yes, good to meet you too.
I think your session was really good.
Oh, okay.
Perfect size exercise, and it demonstrates a lot of nice features.
Yeah, so it should be a nice, easy way to get in. I wanted to say thanks because like I was part of the reason why I know this stuff because I've been going through the books you've been writing.
Oh,
So
right,
it's really handy. All right, so where am I going on this guy?
It's actually a tiny
Oh.
URL. Tiny URL.
Okay.
Datacon Downey, but with hyphens.
Okay.
Hyphens rather than underscores.
Oh, sorry. Do you prefer Firefox versus Chrome? Okay.
Either one should be fine. It's a Google.
Okay, great. Would you prefer it to be cloned on this display, or would you prefer to have it like have your own little
clone is
workspace? Okay, clone's good. So let me just go ahead and. Internet here is kind of slow.
And then, well, that's the same problem we were just having. I thought maybe you were going to have better luck.
Yeah, I had the slides preloaded previously, which was what helped. I wonder if we can plug into this guy. I wonder if the Ethernet cable we could scooch and maybe steal that.
Oh,
Oh wait, never mind. We're getting there.
It's working. It's just
Give it
really
give
slow.
it time.
Okay.
Yeah. Here. Maybe it'll still say loading. Well, you can give yourself an intro and everything to
That's-
start off while it's loading, I guess.
That works. And might. Yeah. Oh, don't do that. Why did it do that? Because it had the URL out.
Oh no.
Oh no, it's still coming.
Okay. My slides are loading slowly, so it'll be a couple minutes, but this is the URL for the slides. So you all can start loading that now.
Wait, don't do it now because it'll take longer to make this happen.
Let's see who gets my slides first, you or me.
Oh. I got batteries now. That's gonna be fine.
And we'll be able to watch your anonymous animals. Like an anteater, a koala, camel, bird. Don't know what that is. And I will start in 3 minutes. While we're waiting for slides, let me get a sense of who's here. We talked earlier during Imran's talk. People who are relatively new to Python, been programming in Python for a while. Okay, good so far. People have used pandas before, not counting the previous hour. Anybody used stats models before? Good. Anybody done regression, linear regression in another environment? Oh, okay, perfect. Anyone done something like logistic regression or some other form of GLM? Excellent, okay.
Let me turn off the auto sleep here.
Great.
What in the world? Give me a second, Alan.
Sure, I appreciate your help with this.
Yeah, where's... Wish it would work right off the bat. There we go. Woke up. Turn on caffeine so I won't fall asleep again.
That's a great beat.
Yeah, it's a great app, right?
Yep. Yes. So what? Just during
Maybe the meat tab, I can look at a table. So, you know, it's spot table.
Oh, yeah.
I can just put it like a table and say, hey, you can go over. And that way the next group can kind of put in a slide.
Mm-hmm. Good idea.
Looks like you guys have got a full house. A lot of people who are interested in learning. Yeah. This is it's still loading slow.
Yes, I think I might start in the non-present mode, which will let me at least look at slides. They'll be small, but that'll get me started.
Oh, so you got two different. You got the slides and you got like the live Python.
Yes. So this will let me show the ones that are loaded. Yeah. Okay.
Kind of. Friday night when I was doing boot camp.
Yep.
I work off of. I have a website where I put all the materials. And so that's the most current. So I'll just use that. Right? I go to load a PowerPoint. So this has been not just like. You know, I should talk to the guys at the front desk because maybe there's something like, you guys pay your
I'll get started now. All right. Okay, let's get started. So I will put the slides in presentation mode. Right now they're still loading. We're going to be able to look at the first few while they're still loading. When I go to presentation mode, it gives me the loading screen. So we'll get started like this. I'll be able to make the slides bigger in a few minutes. But to get started again, so I'm Alan Downey. I teach out at Olin College, which is in Needham. The presentation today is about regression analysis using pandas and stats models. Again, the slides are at that URL. I should have put it on every slide, but it's just at the beginning. So grab it now if you're going to want the slides, or memorize it. Write it down, memorize it, chew up the piece of paper and swallow it. and then we'll be ready to go. I mentioned Olin College. We're out in Needham. It's a new school. We just started up about 15 years ago. Our mission is to fix engineering education. We're almost done. Goals for today. So as I said, we're going to talk about the basics of regression analysis. I'll demonstrate how to do that using these Python tools. And I've got an example to apply it to that I think will be fun. And as you can see in my notes, which you're not supposed to be able to see, this might be a little ambitious. I have probably planned way too much stuff. We will see how it goes. If we don't get through it all, that's okay. The mic is not picking me up. AV people? Help? All right. I'll try to stand close. Oh, that sounds better. I can hear myself. That's good? Okay. I'll stand close. So everything I'm presenting today is from Chapter 11 of the second edition of ThinkStats. The first edition has been out for a while. The second edition is in production now. It'll be out from O'Reilly in a couple of months. In the meantime, the whole thing is available under a Creative Commons license. If you go to thinkstats2.com, that's the second edition, Chapter 11. So anything I say today that doesn't make sense, one option, go to the book and give it a look. All of the code that I'm going to work with today is in the GitHub repo. The repo includes the book itself, the LaTeX source, and all the code that goes with the book. So you can grab it from there. And in particular, in that repo, the file is called regression.py that contains the code that I'm going to be presenting today. So here's the premise. Suppose that you have a coworker who's expecting a baby, and there's an office betting pool to predict the date of birth, weight, and sex of the baby. And suppose that you take this very, very seriously and you want to win this pool. What is all the data that you could use in order to make these predictions? So the intent here, we're going to find data. We're going to find the factors that have predictive value for placing these bets. And we're going to use them to figure out, again, the birth weight, date of birth, and sex of the baby. Conveniently, the Centers for Disease Control has been running a survey for the last 30 years called the National Survey of Family Growth. They have accumulated about 60,000 respondents now, and they've asked lots of questions about family life, marriage, pregnancy, fertility, and so on. So this great data, freely available to download. So we want to find some factor that are going to help us. We're going to start with birth weight and find some factor that are going to help us make a prediction. Now, the baseline is if you have to make a guess with no data at all, you would just guess the national mean. That would minimize your mean squared error. So 7.3 pounds is your baseline predictive strategy. And if you do that, your root mean squared error would be 1.27 pounds. So you would expect to be off by about 1.33 pounds on average. The question is, how much better can we do taking advantage of all the background information that we might have? So a couple of factors to take into account. First babies tend to be lighter than subsequent babies. The birth weight is related to the mother's age. You might also think maybe it's related to the mother's weight. Maybe it's related to the father's weight. Maybe big fathers tend to have big babies. Diet, if you have information about that. Income, general health factors. So we're going to search for factors that are going to provide predictive value, and we're going to use linear regression to take into account multiple factors at the same time. Starting out simple, I'm going to start with what's called simple linear regression. That means that there's only one dependent variable. The dependent variable is the thing that you're trying to predict, in this case birth weight, and only one explanatory variable, which is the factor that you think has predictive value, and we're going to start with the mother's age. And as with all data analysis, you should not break out things like linear regression or any other statistics until you find a visualization that lets you see what's going on with the data. With something like this, one predictive variable, one dependent variable, a scatter plot's a fine example. And if you squint at that, you can see that there might be some relationship there where older mothers might be having heavier babies. It's not entirely obvious from looking at the scatter plot. An alternative to a scatter plot is something like this, where you break the data into bins along the x-axis. So I group this by age, looking at 1-year bins. And then within each bin, I've plotted the percentiles of weight. So this is the 25th, 50th, and 75th percentile as a function of the mother's age. And what you can see is something that looks like an increasing function until you get to the upper end of the age range. And then it's not as clear what's happening. There's not as much data there, so we're not sure whether that's small numbers or whether there's something going on. But what that suggests is, yeah, there does seem to be some relationship between age and birth weight. Starting out with a linear model is probably not a terrible choice, and then we'll have to think about whether we want to come back and add additional factors. So I mentioned, again, simple linear regression just means that there's one predictive variable and one dependent variable. This is the image from Wikipedia that just shows you've got a scatter of blue points, and the goal of linear regression is to find a line that goes through those points that seems to summarize the data as well as you can with one straight line. One way to formulate that is if there really is a linear relationship between these variables, then we expect a mathematical model that looks like this. Each of the things we're trying to predict, which is birth weight, is going to be a linear function of x, which is the mother's age. So alpha is the intercept, and beta is the slope of that line. And then because the world is not perfect mathematical functions, we have an error term, epsilon, which is a bit of a catch-all. And what that error means is things that are actually errors, like measurement errors. So this is survey data. Someone might not report accurately, or the score might not get written down accurately, or errors might be introduced along the way. But it also includes things that are not errors in that sense. It also includes variables that are not part of your model, so unknown factors, or things that are just random, things about the world that we can't predict. So that's the linear model that is the underlying assumption of linear regression. The next step is to try to figure out what those parameters should be, alpha and beta, the intercept and slope of that line. The notion is that if you choose the right line, then alpha and beta should capture a large part of the relationship between these variables, and the leftovers, which are called the residuals, those error terms, epsilon, should turn out to be small. In other words, if you choose the right values of alpha and beta, the errors should be small. So one strategy is to choose the parameters that minimize the errors. There are a few ways to do that. Usually, you minimize the sum of the squared errors. Now, I say usually, it is so common a choice that we sometimes forget that it was a choice. So linear least squares is one way of doing linear regression, but it's not the only way. But it is what I'm going to do today. The question is how? Turns out one of the reasons that minimizing least squares is a good option is that it's computationally tractable. It's pretty straightforward to set up a system of equations and then use matrix operations to solve that system of equations. This is an example being done by a 2x2 system by someone that people in the room might recognize. Does anybody know who that is? That is Gilstrang, Professor Gilstrang at MIT, the guy who taught me linear algebra. And he's still at it. We are not going to solve these equations on a blackboard with chalk. We are instead going to use computational tools, it being the 21st century and all. In particular, we're going to get all the data into a pandas data frame. We're going to use stats models to fit the models, and I'm going to talk a little bit about how you then look at those results and figure out what that means. So as I said, the data from the National Survey of Family Growth, the NSFG, is all available on the web from the CDC. I've downloaded it all. It's also part of the repository if you download that. There are two files there. 2002 FemPreg is the pregnancy file. Contains all the information from the respondents about all of their pregnancies. The DCT file is a Stata dictionary file. It's the data description. It tells you what all the variables are, what format they're in, and so on. And then the DAT file is the data file that actually contains the data. It is not in a nice, convenient CSV format. One of the nice things about CSV is that it has the column labels on it, so you can read it in a single line into pandas, and it makes a data frame, and everything's great. We have to work a little bit harder because it's in what's called a fixed width file format, meaning that there's one line per record, and the records are broken up into fields, and all of the fields have a fixed width, so you can find the fields you want just by indexing into that line. So I need to do a two-step process. I have to read the dictionary file in order to find out the names of the variables and the indices where they are in that fixed width record. And then I'm going to use a function that I wrote called read fixed width to actually get the data. That function is a one-liner. Here's what it does. It just turns around and it calls the pandas function read FWF, which is fixed width file, and then I have to give it the names, the call specs. Those are the indices where each of the data fields can be found. And names is the names of the variables. So I had to work a little bit harder to get a data frame, but once I've got it, I've got one record per pregnancy, one row per pregnancy, and one column per variable. And here's what that looks like. You notice I also used IPython for this. So I display the data frame. Each of these rows corresponds to a pregnancy. The first column is case ID that identifies the respondent, the woman that this pregnancy corresponds to. And pregnancy order, preg order, is which pregnancy that is for that woman. So in this example, the woman with case ID 1 has reported 2 pregnancies. Those are the first 2 rows. The woman with case ID 2 has reported the next 3 pregnancies. So that's what that format is. You can see there are a lot of unused data columns here, but some of the ones that we're going to look at today are things like N burn live, which is the number born alive that came from this pregnancy. And as you can see, just as it turned out, one of the first pregnancies in the data file turned out to be triplets. And hence the multiple birth field indicates that, yep, that was a multiple birth. Okay. Good. You can think of a data frame in 2 ways. The natural way to think about it is as a matrix that has one row per record and one column per variable. You can also think of it as a map, and it's a map from the name of each variable to a column, where a column is in Pandas language called a series. Not that kind of map, but rather this kind of map that says if you have a data frame bracket name of column, the result then is the series. So this is the age at the end of the pregnancy for each of the pregnancies in that data file that we were just looking at a second ago. So the first woman that we looked at who had had 2 pregnancies, those pregnancies were at ages 33 and 39. The second woman at 14, 17, and 18, which is, wow. Let's see. Okay. Some of the operations on data frames that you've already seen, I'm going to use these to select down the data that I want for the predictive task at hand. So the first line here says that I'm going to select all of the records for which df.outcome equals 1. 1 is the code for live birth. So this is selecting all the rows for pregnancies that ended in live birth. For the second line, I'm going to select all of them for which the pregnancy length was greater than 30 weeks. So for the office pool, I'm assuming that the premise of my task is that we are currently at the 30th week of the pregnancy, and you are making your predictions at that point. So I've selected all of the pregnancies that have duration 30 weeks or greater, because that's the point where I'm making my prediction. Next thing I need to do is get rid of the lines that I can't use because the data are not available. So I'm going to use drop na, which is drop NA, drop non-available data. And I'm going to specify the columns that I need. So I need age preg and total weight in pounds. That's birth weight and age at pregnancy. So now I've got a data frame that only contains the valid data, and I can make a scatter plot by extracting the 2 columns that I need. You'll notice I've actually snuck a little bit of syntax in there. In the previous slide, I used the bracket notation in order to select a column from a data frame. You can also use dot notation to select a column from a data frame. They do exactly the same thing. They just provide a little bit of syntactic sugar. The only catch is that you can only use dot notation if the column name is a valid Python identifier. If it has a space in it, or if it begins with a number, or other things that would break Python, it doesn't work. Let me pause there for a second, see if there are any questions about things I've talked about so far. It's good? Yes, sir.
If I'm being correctly, then you can compress these 3 lines of code into 1 line of code.
Absolutely. I could have compressed these lines into one line or one big expression. Yep.
And when you do drop NA, I'm assuming that you're going to retain only those records that like all of it that don't have any value. So you're going to drop a large number of. So basically, you're going to drop any row that has any value.
Good question. Am I going to just drop NA, drop any row that has a NaN value in it? By default, yes. And so that would end up eliminating practically all of my data. The subset parameter here tells me, no, I only want you to drop a row if one of these 2 variables is unavailable. And that's not too bad. I don't lose too much data by doing that.
So basically, the way to look at this is actually that kind of initially I'm kind of focusing on a subset of the column, and on that I'm performing the any operation.
Correct. I'm going to focus on a particular set of columns. I'm only going to drop the relevant ones, right? And then I make a scatter plot, and that's the scatter plot that I showed you a little bit earlier. So you've now seen all the code that generated that figure. Now, let me see what happens if I switch to present mode at this point. See if I have all my data yet. Yes, okay, good. So I'll have big slides from here on in. Okay, a couple of other data frame operations. If you select a column, you can apply things like mean and correlation in order to compute some summary statistics. So the mean of age at end of pregnancy is about 25 years, and the mean total weight at birth is about 7.3 pounds. That's the national mean that I told you earlier. That's your baseline guess. If someone asks you to guess the weight of a baby, you should guess 7.3 pounds. And then the one thing that I wanted to check out quickly is whether there's a correlation between these 2 variables. So this is just a straightforward Pearson's coefficient of correlation, and it comes in at about 0.07, which is a weak correlation, but it is statistically significant. I'm not going to show you how to do that test right now, but I'm just going to assert that it is, but relatively weak. Okay. All right. Let's get on to actually doing the linear regression. So as I said, I'm going to use stats models, which is one of these nice modules that Python provides. If you installed Anaconda, you got stats models with it. So you've already got it. One of the things I love about Anaconda is that you do not have to wrestle with installing all of these things individually. I teach this stuff in my classes at Olin. So if the students are having headaches with these things, then I have headaches with these things. And Anaconda has greatly reduced the number of headaches that I'm dealing with. Stats models actually provides 2 APIs for working with regression. One of them is more matrixy, and one of them provides a more formula using these string formulas. So I'm going to use these. These strings that I'm going to show you in a second are actually in a syntax that's called PATSI, which is a way of specifying a model, specifying a linear regression model. So I'm going to import that as SMF, which stands for Stats Models Formula API. The formula in this case is the simplest one you can do, which is a dependent variable, total weight lib, total weight in pounds. Squiggly means I'm going to run a regression with this as the dependent variable and the following list of explanatory variables, which in this case is just one, age preg. Then I'm going to run smf.ols. OLS stands for ordinary least squares, which is one of the ways, as I said, of doing linear regression. I need to specify the formula. I need to specify the data frame that the data will come from. When you run OLS, what you get back from that is a model object. And then when you run fit, what you get back from that is a regression results object, which provides summary. And if you are running this in IPython, you get that summary in a nice graphical format. If you're running on the command line, you get it laid out nicely in text. If you're running in IPython, you see something that looks like this, which if this is the first time you've seen linear regression, that's a lot of stuff and you kind of run screaming from the room. Don't run screaming from the room. Let me break this up into a couple of steps. The middle block there is the one I'm going to focus on first. This is the result of the regression. These are the estimated parameters. So there's one row in this table for each of the parameters that you estimate. The intercept is the parameter alpha in my mathematical notation, and agepreg is the slope associated with the variable agepreg. So the column that's labeled coef stands for coefficient. That's the estimated parameter. In this case, the intercept is about 6.9 pounds, and the slope is about 0.01 or 0.02 pounds per year of mother's age. Right? Not so easy to interpret. I'm going to suggest in a second a way of making these things easier to interpret. Standard error and the confidence interval are ways of quantifying the uncertainty associated with these estimates. I'm going to tell you more about that in just a minute. The t-statistic is an intermediate result that is used in order to compute the next column, which is the p-value. What the p-value tells you is the probability of seeing values like this if, in fact, there were no relationship between these two variables. That's what that output means. I'm going to go back and explain each of those things in a little bit more detail. So first, interpreting the slope and the intercept, you can unpack them. The results object has a field called params that you can pull the estimated parameters out of. So I've got inter and slope put into variables that I can work with. Again, as given, they are 6.9 and 0.016, but it's a little hard to get your head around that. First of all, that intercept, that is the average weight of a baby if the mother is 0 years old, which is just kind of a weird number to try to get your head around. So one of the things that I suggest is rather than report the intercept at x equals 0, I find it convenient to report the intercept at the mean value of the x-axis. In this case, the average age is 25 years old, and 7.3 pounds is the average age of a baby if the mother is 25 years old. So that's a more meaningful number to report. The other thing that you can do, especially with very small slopes, is express them in units that people can understand. So instead of pounds per year, I'm going to put it in ounces per decade. And that gets me up to a number like 2.7 that tells me, okay, so if a mother is 10 years older or 10 years younger than the mean, I would expect that baby to be 2 or 3 ounces heavier or lighter than the mean baby. Okay. So that's my suggestion. Anytime you're presenting the results of linear regression, try to express the intercept and slope in terms that human beings can understand. Standard error, I just wanted to give a rant on this topic, or maybe it's more like a gentle reminder. It's not a rant. What standard error tells you, and the confidence interval as well, is they're telling you about variability that's due to sampling. Another way to think about that is if you ran this experiment over and over, in other words, if you went out into the general US population and recruited 9,000 respondents and recorded their results, if you did that experiment repeatedly, you would expect your estimated parameters to vary from one experiment to the next. Standard error and the confidence interval tell you how much you would expect those values to vary if you do the same experiment again. Now, that's nice. That's a way of quantifying one part of the uncertainty about your estimates, but it's only one part. So for example, it doesn't tell you anything about measurement error. If you have consistent errors in the way you measure things, that will not be part of the output from linear regression. And then the other is if you have sampling bias. If you are consistently selecting people from the population in ways that throw off your estimated values, again, standard error is not helping you with that. Okay, that's my friendly reminder about interpreting standard errors. The next part of the output, this is the big block that was on top of the output. Some of this, the left-hand column is mostly just telling you things you already knew, like when you ran the regression and how many observations there were. There's a little bit of the DF stuff is about degrees of freedom. I'm not going to talk about that today. The thing in the upper right-hand corner is frequently a useful result. That's the R-squared value. What that's telling you is the fraction of variability in the dependent variable, in this case birth weight. So the variability in birth weight that can be explained using these explanatory factors. In this case, 0.005 is a very small fraction, meaning that the explanatory variable here is not actually telling you very much about birth weight. Your guesses are not going to be very much better taking this into account than they would have been if you didn't take them into account. Okay? We're going to see in a minute if we can do better. Yes, sir?
In R, we have this 1 star, 2 star, 3 star, an easier way to discard or achieve a particular dependent variable. So we have something like that here. I don't want to go through that the probability value versus the stars.
Yes, we'll do that in a second. The question is, in lots of environments, the estimated parameters and the model might be indicated with stars to tell you whether they are statistically significant or not. There is a version of that here, although I do want to distinguish between R-squared, which is a measure of how much variability have you explained with this, and the stars, which are statistical significance. Those are related to the p-value. In this case, the field here that says the prob of the F statistic, that's the p-value. What a p-value means is, if these values were not actually related to each other, what would be the probability of seeing a spurious result as big as this one? Okay. In this case, it's extremely small. It's about 10 to the minus 12th. So what that says is that these results are very unlikely to be explained by chance. In other words, they are statistically significant at a very high level of confidence, which is to say the p-value is very, very small. However, the R-squared value is also small. These two things often happen together, and people are often confused initially when these things happen together. So the small p-value means that this relationship is probably not due to chance. It is statistically significant. The small R-squared value means that the mother's age does not account for very much variability in birth weight. Okay? So it's a legitimate model in the sense that it's statistically significant. It just does not have a whole lot of predictive value yet. We're going to do a little bit better in a minute. Yes, sir? Is that the same as the model's power? That one's going to be a little complicated to untangle. I'm going to punt that question for now. Okay. You guys jumped right in with questions at exactly the right time. So I'm going to add some more factors in a minute, but before I do, this is a good time to clarify anything left over. The reason I punted power is a little bit ambiguous. If we're talking about predictive power, then yes. If we're talking about the power of a test, that's a different statistical concept. Good. Okay, we started with simple regression, meaning there was only one explanatory variable. Now we extend that to multiple regression. Still, one thing that we're trying to predict, birth weight, but lots of variables. And this is the mathematical notation. I still have the intercept, beta 0, but now I've got multiple factors, x1, x2, up through xn. And for each factor, I'm going to have a linear slope associated with that factor, and then again a residual term or an error term that captures random stuff or anything that's not included in my model. That's the mathematical form. Here's what it looks like in code. The only change I have to make is I'm going to add more factors to the formula. and I'm going to use the plus to say I'm adding up a whole bunch of linear factors. So now I've got my dependent variable, total weight, and two explanatory variables, age, pregnancy, and is first. Is first is a binary variable. The way I'm going to make that is I'm going to say live.birthord equals 1. Birthord is birth order equals 1 means first baby. So that's a Boolean value. And then I'm going to create a new column in the existing data frame that's called is first. And again, I'm going to run OLS. The result from OLS is a model. And then I run fit. The result from fit is a regression results object. And then I can look at the summary. From the summary, I've pulled out just the pieces we're going to look at. Yes, sir?
If I may, what's the reason behind you using binary variables instead of live birth order?
Binary instead of?
Live birth order, that's 1, 2, that would be categorical 1, 2, 3, or 4, and you're making it binary.
Correct. So I could have, if I used live.birthord, that would be an ordinal variable. And what that would try to do is predict birth weight as a function of birth order. If I think that's a linear thing, if I think that the second baby is heavier than the first and the third baby is heavier than the second and so on, then that's exactly what I would do. We're going to see an ordinal variable in just a minute, so you'll see an example of it. In this case, the reason I chose this is that I had prior data that showed that first babies compared to others were a bit lighter. And so I just made it into binary categories.
But you didn't have any theoretical explanation if third baby is much heavier than second.
Right. Right. Okay, here are what those results look like. So the R-squared value got a little bit better. Remember that it used to be 0.005, and now it's 0.006. So you might think, oh, that's great. I added a variable, and R-squared got better. However, remember that if you start adding more and more explanatory variables, you would expect your R-squared value to get somewhat better just by chance. And that's what the adjusted R-squared value does for you. The adjusted is adjusting for the fact that you've added more variables. And what it's doing is comparing this model with two variables. I'm being a little loose with the definition of this, but what it's accomplishing for you is telling you whether adding that new variable did more for you than you would expect by adding a totally random variable. The answer in this case is no, because the adjusted R-squared value is still 0.005. Okay. We also can see that in the estimated quantities. There is a coefficient associated with is first. It's negative, which means that if it is a first baby, it will be a little bit lighter. The p-value is now about 0.109, which means that there's about a 10% chance that I would have seen a coefficient as big as that if, instead of using real data, I had just put in a bunch of random numbers. 10% is kind of iffy. 5% is usually the magic borderline. Anything below 5% is magic. It's statistically significant. Anything above 5, no, not statistically significant. So 10 would not normally be considered statistically significant, and in combination with that small R-squared value probably means that knowing whether it's a first baby or not doesn't actually help. So that's one of the conclusions to draw. We're going to look for more factors in a minute, but I do want to loop back. Do you remember when I showed you, let's see, did I put this curve? There we go. We looked at this curve, which suggests that the relationship between age and birth weight might not be a linear relationship. So one of the things that we could do is add a quadratic term. So I'm going to compute a new column called age2, which is equal to age preg squared. And then I'm going to add that to the linear regression. Any questions about this slide? Yes.
Is it all like information that came up with this variable based on some prior knowledge, or is it like sort of, let's say, try squared and then?
Good question. The question was, is this totally hit or miss? Am I just totally making things up? I added squared. There is actually some rationalization, or maybe it's a rationale. You can decide whether it's a rationale or a rationalization. If you look at this, a parabola is not a horrible idea to fit this data. So from a mathematical point of view, the shape is about right. Also from the point of view of a Taylor series, you can imagine that any function can be approximated linearly. And if the linearly isn't good enough, well, then you go quadratic. And if that's not good enough, you can go cubic. So some combination of, yes, this is well-founded, but also there's some art to it of exploring and trying stuff out.
You can also go the other way, right? Try reducing, like start with a big set and start reducing variables.
Could have started with a big set and worked my way down. Yep. Yep. Yes?
So as you're trying these different models, are you basically just looking at R squared to figure out which one's the best predictor and go from there?
Great question. So as I'm trying out different models, am I just looking at R squared? Yes, that's one of the indicators of the quality of the model. There are some of the others, like AIC is an information content, the IC part, information content metric, that's also useful for comparing models in a little bit more rigorous way. I'm not going to talk about the details of that today, but that would be a good thing to look at into next. The other thing I'm often looking at is also what are the estimated coefficients? How big are they? Because that's telling me whether this is an important explanatory factor or it might be really small. And the p-values that are telling me whether it's likely to be due to chance or not. Yes?
Why are you leaving the original age?
I'm leaving the original age because now I'm going for a full parabola that's going to be a function of both age and age squared. All the way in the back.
Given that you've got libraries that do a lot of the heavy lifting of the math of these calculations, and that it seems like there's a standard set of types of curves, types of things you're throwing at the wall, isn't there something that automates throwing those things at the wall?
So the question is, I'm kind of doing this exploration by hand, but there should be automated ways to do this, and in fact there are. I'm going to take a step in that direction in just a minute, and then there are, within machine learning and data mining, there are even more rigorous ways to go about this. Yep.
Are there other than in an academic setting, in a learning environment, is there a reason to do this as a manual process nowadays?
Good question. Is there a reason to do this manually? I do think that as a researcher, you get some insight into the data by walking around in this space and trying some things, visualizing results. I do think that you can develop understanding of the data that might be hard to get from a fully automated process. But I'm a big fan of complementary tools and also people who come at it from different approaches. I might find stuff with my approach that somebody doing data mining might miss, but vice versa as well. They're going to find great stuff. So I think it can be a complementary set of tools. Let's take a look at the results from this. The R-squared value is a little bit better. Even after adjustment, it's a little bit better. And if you look at the p-values, they are all very small. They're not actually 0. It's just that it's reporting the first 3 digits, but they are all highly statistically significant. So that suggests that this quadratic model is not a terrible idea.
I would add, if you're trying to make a statement about causation, what is causing the
Yeah.
birth rate, and if you run 20 tests, you're going to expect that one of those is going to come up as a positive test just by chance alone, because you set a p-value of
Yep.
0.5%. So if you know in advance and you're really interested in these particular, I think these particular predictors are of interest, that makes a much stronger case about causation to specify those in advance, run that particular regression, than to throw it over.
Shotgun. Yeah, that's great. You actually made 2 really important points that I'll try to paraphrase. And one of them is, if you are trying to make a claim about causation, you often want to go about this in a more careful way. If you take this shotgun approach, you are very likely to get false positives. That's the second point that you alluded to. And if you go run a whole lot of tests, find one of them that's statistically significant and declare that it must be a causative factor, you are very likely to be kidding yourself. So that's a very useful caution about this whole approach. Good, we looked at that a second ago. One question that comes up when you start throwing in quadratic terms is, wait a minute, I thought you told me that this was linear regression. How is it that we're fitting a nonlinear model to the data? It is still a linear model. One of my factors happens to be the square of another one of my factors, but it's still a linear combination of those factors. So even though it seems a little bit weird, this is still linear regression. That is not linear regression, that's linear B, which is totally unrelated. Okay, now let's get to the mining part. The data file that I'm working with has 1 record per pregnancy, and there are 244 variables. There's another file that's available, which is the respondent data, which is the general background for each respondent, and it contains about 3,000 variables for each respondent. So thinking about how many variables I have to work with, some of them must have predictive value. I do have to play by the rules, which is that I can only use a variable if it is something that I would know during the 30th week of pregnancy. So for example, one of the factors that turns out to be predictive is whether the baby is breastfed or not. But I don't know that during the 30th week. The other is I'm going to play by the rules that things that you would credibly know about a fellow office worker. So a lot of them are very personal details that I'm going to assume you don't know. In order to, as I said, I've got 2 data files. One of them is indexed by pregnancy. One of them is indexed by respondent. In order to run these regressions, I need to join these 2 data sets so that I have one gigantic data frame that has all 3,200 or I guess 3,300 variables in it. And here's how I'm going to do that. I'm going to read the respondent file. And that's very similar to the code that I showed you earlier for using the pregnancy file. And then I'm going to set the index for that so that it is indexed by case ID. This is a performance hack that makes it fast to look into the respondent file and find the respondent that has any given ID. Because what I'm going to do now is a join. And what the join is going to do is it's going to loop through each pregnancy. For each pregnancy, it's going to grab the case ID. It's going to use that case ID as an index into the respondent file, grab all of the respondent variables, 3,000 of them, and join them, append them onto the row in the pregnancy file, so that now I'm going to have 1 row per pregnancy, and I'm going to have all 3,300 variables in one gigantic row. And I'm going to do that with 1 line of Python. Because that entire operation that I just described is a well-understood database operation that's called a join. And all I have to do is tell it the 2 tables that I want to join and the index variable that I want to use to map from 1 row in one data frame to the corresponding row in the other data frame, which is the case ID. So I'm doing a join on case ID. That's why that parameter is called on. If you know SQL, that should all sound very familiar. If you don't, you're just mashing up 2 data frames. Questions on that? It's remarkably efficient. For the 8,000 records and 3,300 variables, this takes about 2 seconds on a not very impressive piece of hardware in my office. Okay. So again, thinking about an automated approach to looking for relationships here, I'm going to try all the variables pairwise. So I'm going to do simple regressions with just 1 explanatory variable at a time and birth weight as the dependent variable. And I'm going to select all the ones that come out with strong predictive value and that don't seem like they're totally crazy. When I look up the variable and it turns out to be something that just couldn't possibly be right. Here's what I came up with after a fair amount of adding and removing and deciding which factors. Again, age pregnancy turned out to be useful. I dropped the quadratic term. I added race, which did turn out to have some explanatory value. The C parenthesis race means we're treating that variable as a categorical variable. In this particular data set, it's coded as 1, 2, 3 for black, white, or other. And we'll see in a second what the results look like. N born alive, we saw that earlier. That's the number of babies born alive at the end of this pregnancy. If that's greater than 1, that means it's a multiple birth. And multiple births tend to be lighter. Each of them is lighter on average. Pay DU is a weird one. That is I've turned it into a binary variable. That is whether the respondent owns her house. Kind of weird. It's probably a proxy for other economic variables. Economic variables influence everything. It's sort of a notion in all social science that income and other measures of wealth and things like that are always explanatory. In fact, I ended up with 2. Total income of respondent is the other. Questions about the variables? I'll show you the results in a second. Yes, sir.
That means there will be interaction.
There will be interaction between variables, right? So, for example, income and whether you own your own house are probably different measures of some factors in common. They might be partly collinear. And if you have multiple variables that are very collinear, then things start to go badly because the estimation process becomes underdetermined. And from a linear algebra point of view, solving that system of equations becomes ill-conditioned. And systems like this will often give you a warning when that's happening. In this case, these 2 variables apparently contain enough independent information that the estimation process is discriminating between them.
So then, would you set up a regression model or whatever model between those variables first, if you have that instinct beforehand?
Yes. So in this case, I tested each of them independently, and they both seemed to have predictive value. And then when I put them together, one of the things that can happen is that one of them can clobber the other, or they each can dilute each other. In this case, when I put them together, they both seemed to have good predictive power, so I kept them both. Individually they did, and after I put them together, they still did. Yes?
Do you support so does it support the forward subset selection or backward subset selection, thereby you incrementally add variables to improve your R-square? That way, the system, the procedure also allowing you to kind of get rid of the multicollinearity consideration. Do you have that support in the package?
That's a great question. Can I put that one off for now, because you've introduced a few things that we haven't got to. Yep. Good. Let me show you some results from this model. So again, as I'm doing these things iteratively, one of the things that I'll do is scan the column of coefficients to see whether it's making sense. My intercept is still around 6 or 7 pounds. The categorical race variable, the default is usually whatever the lowest value is in whatever the sort order is. So the default in this case is race equals 1, which is black. T2 means the quantity 2, which is white. T3 is other. And what this is saying is that relative to the baseline of black mothers, white mothers are having babies that are about 1/3 of a pound heavier, and other races are about 1/3 of a pound heavier. And that's after controlling for the other variables here, like the income that I mentioned, number born alive. So each of these has values that don't seem completely crazy. Multiple births are about 1.4 pounds lighter, which is pretty substantial, but consistent with what we know about multiple births. The other factors are relatively small, but scanning the p-values are all very small, which is saying that these are statistically significant, just means they're unlikely to be due to chance. The R-squared value for this model, this is pretty much the best model that I found. I didn't work super hard, but after poking around a bit, this was the one I found. 0.047 is still quite small, but remember that we started with 0.005, so it's about an order of magnitude bigger than what we started with. The root mean squared error with this model, which means that if you use this model to make many, many predictions, you should expect to be off by about 1.23 pounds on average. Remember that our baseline strategy was always guess the mean. If you always guess the mean, you'll be off by about 1.27 pounds. So we win a little bit. This is an example of a model that has lots of statistical significance. So these effects are likely to be real in the sense that if you run this experiment over and over, you will probably see these effects. However, the effects are relatively small and don't have a lot of predictive power. I got a question in the back with a red shirt. How did I calculate the root mean squared error? So one of the things that comes out of the model is the residuals. The residual says that if you generate lots of predictions, the residuals are how much you're going to be off by, and the standard deviation of the residuals is the root mean squared error of your guess, of your predictions. That is part of the output. In fact, if you do results.resid.std for standard deviation, that'll do it. Yes?
You don't report the adjusted R-squared?
I don't report that just as R-squared.
The adjusted R-squared?
Oh, sorry, I did not report the adjusted R-squared. I don't remember what it was. It was not bad. If there's a big difference between R-squared and adjusted R-squared, that suggests that you've got factors in the model that are just contributing noise. As I recall, that was not the case. Okay, let's see how we're doing. Sorry, I completely lost track of time. We started a little late, and I'm already past my allocated time. We got through linear regression. We didn't get through logistic regression. I will have to punt. I'll wrap up quickly. Feel free to go through the slides. You can learn about logistic regression. This was what I used in order to predict whether the next baby will be a boy or a girl. The results are similar. You do a little bit better with the model than without, but not by a huge amount. There's a summary in here. I talked about linear regression. There's more information about logistic regression. Logistic regression is used if the thing that you're trying to predict is a binary variable, like a boy or a girl. You can do Poisson regression if the thing that you're trying to predict is a count. For example, this model predicts how many babies a woman has as a function of age squared, and in this case it turned out to be the cubic model, worked pretty well, race, income, and education. Multinomial logistic regression lets you predict a categorical variable. So if you want to guess someone's marital status based on other information, this model would do that for you. And then last, if you have an ordinal variable like Likert scale, if you want to predict whether someone likes frozen yogurt or not on a scale of 1 to 7, you could use ordered logistic regression. But if you want to do that, you're going to have to write it yourself because it's not in stats models yet. That is it. I just want to give you a couple of pointers. Again, this is all in ThinkStats. You can read the draft now, and the published version will be out in about a month. The code I mentioned is all on GitHub. If you search for me, you'll find it. I write a blog about various statistical related things. So if you check out Probably Overthinking It, you can read more of this stuff. I wanted to make a quick mention. I'm teaching a class in the spring called Data Science. I'm going to have student teams who are interested in working with external collaborators. So if you have some data and you would like a student team to do some exploratory data analysis and help you find interesting stuff in there, you can check out last year's projects to get a sense of what we're doing, and you can contact me. There are 4 ways to contact me, and the URL for these slides. So sorry I ran a little over. Can we take a minute? Oh, and I should say the nice people at O'Reilly have sent along some copies of Think Python. So if you're a Python beginner, this might be a nice one for you. And I think John has a way that we're going to raffle off or give tickets, or what's our system? The first people that get to the table?
Oh, God. What's the fair way to have a random number generator that loves Python or...
Yes, if you ask a question during this talk, you get priority. And I think John has set up a table, so we'll take a break. I'll be over there. If you have questions, come talk to me. And if you would like a copy of the Python book, come talk to me. Thank you all very much. Sure.
So in R, you have multiple ways to write a formula. Like you have a dot formula. The dot will include all the variables. And then you have a dot minus the variables that you don't want.
Interesting. I don't know. So the syntax that I'm using here is called Patsy.
Yeah.
If you want to look up Patsy, that'll tell you.
Okay.
It might be the same syntax as R.
Good, but I really like it.
Good, thank you.
Hi, so I'm a social scientist, so basically we need to produce a LaTeX table to publish our regression results into papers. So is there any libraries or set of code that I can use to automatically put the result from this table to LaTeX?
I haven't seen one built in. I have written something that reads the results and generates LaTeX. And it's only about 10 lines of code.
Okay.
So you can do it yourself, or you can find it in regression.py.
You're like a GitHub.
In my repo. Okay, thank you.
So, for those folks who want to have, there's actually a room that's a nice cozy room that has green chairs and a table and like a living room. I think that would work a lot better because we've got sponsors over here. So, if I think that would be perfect actually. So, thanks guys.
Is that the one that's right here at the screen?
Is Andy in the house, or is he out in the hall? All right, I will track him down otherwise. So we'll be starting here in a second. Any questions? Let me know.
I ask everyone to speak to the same question. Would you like to be recorded or yes, please?
the other thing too is
There's always that.
yeah, there's if your handheld. If you want to, is that not working?
I don't know. I didn't. Do you know how to do it?
Just the power switch should be here. Put it to your, see if it works. It sounds like it's on.
Hello. Okay.
And then just flip it onto your.
Thank you.
Oh, that's just a timeout for the.
Oh God. How do we do that? Let me get my charger. Okay.
Well, it's funny because I was going to set the speaker. And so this section's got a couple talks. Each one
Yeah. We.
you guys talk adjustment back here, so you guys
Yeah.
kind of all
So
figured it
he's
out.
gonna wave at me when I'm 15 minutes in, and when it's like, or
Oh, yes,
basically he's gonna give me
oh, you
advance
guys-
notice, right?
Right. So he's got it all set. Okay, cool.
So. Okay, so you guys want to get this started? Or should we wait? We'll just wait for like another minute. So, everybody, other people's data. So, raise your hand, everyone, if you've ever hated a data set. Like, viscerally, keep you up at night, kind of. And raise your hand if it was data that you collected. Okay, that's actually surprising, because usually it's like, when you're collecting it, you know what you're going to do with it, right? So you kind of pay attention to all these things, but when it's someone else's, God knows, like any government data people around here, for example, that's kind of a problem. So I'm Mali. I work at the Harvard Center for International Development, and we basically look at developing countries and why certain countries develop better and why they don't. And more microphone, like this, much better. How about now? Okay, I'm just gonna do this. So we basically study developing countries, and we look at their data and we say, okay, what makes this country differ from this other country? But that's a whole different story, so I'll tell you more about that later. And I come from Istanbul, Turkey. But I love Python, right? And there's a lot of this going on the internet. So economist E86D. There's a lot of kind of people don't understand why Python is so cool for data analysis, because they're like, oh, I can do this thing in R, but you can't do this thing in Python, blah blah blah. And so Python, it's true that there are certain things that you can't do, and Python is still getting there. But Python is really good glue, right? It's really good at scraping data, loading different kinds of data, converting stuff, tying different applications together, doing all sorts of things that a specific data analysis language might not necessarily allow. So I want to show you kind of like a mini demo of what you can do. Okay, so maybe some of you guys may have seen this. So recently there was this thing on the New York Times where it was an article about like how police forces are getting militarized, and they released a data set. And so it's pretty cool that they have this awesome visualization that you can play with. But the data set is also on their GitHub. So I thought, well, why not load that data set up for this talk and show like what kind of stuff is a pain in the butt and how can we like kind of get through this. And there's like a small portion of this and some more slides, so I'll show you guys. So just regular, read Excel works fine. And then the first thing I usually do is I look at the columns. Okay, so like what do we actually have here? There's like a reasonable number of columns. There's a ship date, acquisition costs, fine. UI, not sure what this is quite. NSN, not quite sure about that one either. State, county, okay. So the second thing is there's this cool thing called info, where you can look at every single column and you can say how many things in this column are not null. Because just because you have a table full of 73,000 entries doesn't mean that every single row in the table has 70,000 things, right? So for example, a lot of things are lacking names, it looks like. So then if you really wanted, you could also use describe, which is another really cool thing, where it'll give you some descriptive statistics. So let's say, what's the largest quantity of something, and then what's the smallest quantity of something, and that gives you some idea as to, what is there anything possibly wrong with this data set, right? And so let's look at this. So here's what we have. Can anyone point out things that they see about this data set that could possibly go wrong? Dates, yeah, okay, so dates is a good one. There's like 2 different date formats. So one of them is like this, and the other one's actually like they just merged year, month, date together. So, that's true, yeah, that is weird. Someone said units, that's a pretty good instinct. Yes, so foot and FT, that's a good each and EA. So quantity seems pretty okay. And then, so the other thing that kind of hits me is that there's state and county, and they have the state and county names. But usually, if I had some other data set, like I want to compare like the militarization with the, I don't know, poverty level or something like that, right? Then I'm going to have to like merge that with another data set. And for that, it would be really nice if there was some kind of like number index that I could merge. So if I knew that this was like postal code XYZ or, you know, state code XYZ, but now I'm going to have to like match them by name, which is going to be terrible because some of them are going to be spelled differently and it's going to be a pain in the butt. But yeah, so I'll kind of move into like how we deal with some of this stuff. So you can say, so one of my favorites is this thing called value counts. And it'll tell you basically, I used to do this manually where you group by the number of things and count, and you don't have to do any of that. You can just look at the units and you can say, okay, so there's 51,000 eaches and 13,000 EAs. So maybe it's like a East Coast, West Coast thing, I don't know. There's pair and PR. Somewhat unknown. Someone put, like, actually wrote out the words unknown. At least they were consistent about it. And it looks like, so there's this pattern here, right? Kit and Keat, KT, PG and package. Okay, so, like, what do we do about this? Well, you can use this function called replace, where you can give, like, what column you're going to replace, what value, and what you actually want that value to be. Oh, it looks like I made a mistake here. Oh, the more you know. And you can run this, and let me show you what the data set looks like. Well, here. So what it looks like after. Okay, so this looks much better, right? Now we have each, pair, kit, unknown still there, but set, box. And now it's like at least a reasonable, I see like dozen and 100 here, and that annoys me. I'm like, why couldn't that be just 80 times 12 or 77 times 12 or times 100? But maybe there's a good reason. Maybe, you know, they just bought it in units of that kind of package, and that's like information that they didn't want to lose. So maybe we could create a new column for that or something. But and then, oh yeah, and then the unknown. So so Pandas uses NumPy's nan for unknown values, and so you can just, you know, do that pretty easily. Actually, I don't think you even need to do this, but you can do that. And then so now it seems pretty reasonable. Now if you look at the very bottom, you'll see that there are all these other things, right? There's like a hank, a bolt, a skein. This I'm like 100% certain that E4 right there is actually supposed to be an EA and someone mistyped it, which you know makes me really, really sad that there was no validation going on there. But okay, so we can look at the last 20 things and we can say, okay, there's like maybe like there's like 54 things in here, and it can't be more than 100 items, so maybe we should just throw these away instead of like dealing with them by hand. So I'll do that. I'll actually use this table that got output, and I'll say, okay, give me like the everything after 20 or whatever, and I call that don't care. And then I say, okay, give me everything that's not in don't care. And then, well, I mean, I could show you what that looks like, but it's going to look the same. And then the other thing that you'll notice, the weird thing is that the date column, right? There's multiple different formats. So how do we deal with this? Well, you know, whenever there's formats of things, regular expressions is maybe not always the best choice, but works pretty well quite often. So you can say, for example, well, so before that, there's actually this cool function called PD2DateTime, where Pandas can basically take a datetime column, infer the format, and then turn it into an actual datetime value for you. So your strings would magically be converted, except we're kind of screwed in the situation because we have two different datetime formats. So what do? So you can use this contains function, where you can specify basically any regular expression. So this thing says, okay, give me 4 numbers dash 2 numbers dash 2 numbers. And then this says, give me all those things that have, you know, that kind of format. And then so I basically split the whole row into 2 different things, and I say, okay, you know, dates A, dates B, and then you can put them back together in a new variable and assign them back. And now, well, here, let me actually run all this so you guys can see. That's my fault. I need to delete these parentheses, but it should work fine. Okay, so now we have a column of reasonable looking dates. And they're of type date time, so you can do a lot of cool things. When you're plotting, pandas will be intelligent about it. You can rescale it to be like annual values, and it'll be like it'll be really intelligent about it. And yeah, so this is kind of like what it looks like. But I'm going to show you a bunch more stuff that's actually in slide form. So when you want to read data, Pandas provides you a ton of different ways. Like the read, wow, actually read table's not in there. I blame myself for that. Read table, for example, is really convenient. You can tell it basically, you can give it a file that's split by semicolons or something, and it'll be, you can say, this thing is the separator, this thing is the line separator, and blah, 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 and it'll be really smart. So there's a lot of different formats, file formats that you can use, and this kind of adds into how good Python is as glue, basically. And then there's, you should always kind of know what the string encoding of your file is, or you get stuff like this. And there's a bunch of pretty cool libraries that do that. Unicode data is one where you can take Unicode values and let's say you had cafe with a E with the accent, and you're trying to basically, you're going to use another program that doesn't handle those special characters well. So you can use Unicode data to turn that E with an accent to an E automatically. And there's like actually gigantic tables on like how these characters should be converted to be like the most readable way and all this stuff, and yeah. And then the other thing is the plain old Linux file command will actually give you a reasonable guess as to what the encoding of the file is, which sometimes comes in handy. And then there's another one actually called chardet, where you can point it to a file and it'll say there's like an 80% chance this file is in Windows blah 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 encoding or something like that. Anyway, it also matters to get the right column type. So when you load data up into Pandas, like sometimes it'll take your columns and it'll make them like integers. But sometimes you don't want them to be integers, you want them to be strings, because let's say, okay, postal codes is a bad example, but let's say postal codes could start with a 0. If it thought it was a number, then it would chop that 0 off from the beginning, and you'd run into all these issues. So it's important to like kind of pay attention to that beforehand. And then you can get an overview with info and describe, which. And then you got to look at, like, does the data actually make sense? Like, if you were listening to the first talk here yesterday, it was a very interesting talk about how descriptive statistics can really mislead you. And so visualizing your data is a really cool way of exploring it and see if it's actually sane. So this right here is Anscombe's quartet, where all these different, these 4 graphs, all the dots on them, they all have the same mean. They have the same variance. And so if you were to look at it and you were just to type like, dataframe.describe, they would look exactly the same, right? But when you plot them, you see that they're ridiculously different. One of them is going straight up, one of them is doing a curve and all this stuff. And then you can say, okay, which things in this column are not unique, duplicated, which is pretty cool. It gives you a list of, what you are going to have to fix, basically. And then value counts I showed you guys. There's a bunch of tools to fill in empty data. So you can say, for example, let's say you have a list of how much something cost over the years. If you were missing some data, you could say series.interpolate, and it would basically look at what's before the missing value and what's after the missing value. And it would basically try to give a reasonable estimate as to what could the middle value be. And there's a bunch of different methods that it can do it with. And then there's also a .fill_na, which is pretty cool. You can also say, like, okay, I don't want to guess what the value is. Instead, I want to use like the previous value or the next value. So this makes that really, really convenient. And then there's always, so data sets never live on their own. You always like have to merge them with other things, right? And so this is kind of like a classic data set join where you have a table on one side and a table on the other side, and you have these like little numbers, and you say, okay, field one over here is field one over there, and you're merging them together. And so Pandas has a bunch of pretty cool tools for that. There's dataframe.join and dataframe.merge. So join, they almost do the same thing, except join is more oriented towards like what your index is. So it's more about like if you had two tables that already were indexed correctly and you want to match them, then you use join. But with merge, you can say, okay, use this field from this table and this field from this other table, and put them together. So it's a little more convenient. And then it's always good to like check the column sizes after the merge, because a lot of times you'll lose data while you're merging things, because sometimes the indices won't be correct. So you'll have like 1, 2, 3, 4, 5, 6 over there, and then there'll be like a -2 or something because someone put in some bad data there, and then you'll lose some data. So good to watch out for that. Okay, so the other thing is, so what do we do if like we're merging a data set together and we don't have the 1s, 2s, and 3s, or like the data set we have only the state names or something? Then you have to do some, well, if they match perfectly, then you're in luck. It's a unicorn. But if sometimes you'll have to do fuzzy matching. So what that means is you have to say, okay, like these two things are probably the same thing. So actually, there was a good example, but I'm not going to pull that back. But like in the data set, there was this example where it said, rifles 5-point-something millimeters, and then there was another one that said rifles 5.6 millimeters, open paren, like I forget what it said. But the point is someone added some data at the end, but those two things are the same thing. So there are a bunch of tools and libraries that let you kind of look at the probability of matching of two things. And Jellyfish by the Sunlight Foundation is a really, really awesome tool that does that. The other option is if you have something like Elasticsearch or Lucene or Solar, any kind of like text, full text search database thing, you can kind of like load your data up in there and let that do the matching, which I find to be kind of a pain in the butt, but it works. And then, so this is a little more esoteric, but there's a lot of situations where you'll have classifications of things. So I'll be looking at, I don't know, like what products a country exported. And, in 1997, they'll have this classification system where like they'll have computers and telephones, and they'll have all these pretty numbers. So it'll be computers are number 1 and telephones are number 2. And then like a year later, they say, oh God, computers is getting too big. We got to like split these things up into multiple categories. And now you have desktop computers and portable computers. And now they're like, now the numbers of previous year don't work this year. So what was number 1 now split into like number 1 and number 2. And so this is like a whole huge pain in the butt where you have to like deal with this problem. And you can do some very interesting things where you can load these data sets up in NetworkX, which is a really awesome Python network visualization tool. And you can say, okay, like you can visually inspect like which categories went into which other categories, which is really, really handy. And then you can do some more advanced stuff where you can say, I'm going to like, I don't care whether computers are split into desktop and portable computers. I just want to merge them all together. So there's some stuff that basically does that for you. And then there's a lot of stuff I find myself doing when I'm writing like longer notebooks where I have this problem. It's like long line-itis where I'll just like add stuff, do this, do that, merge, join, filter. And then I'll end up with these lines that are like gigantic. And I'll be copy-pasting things around. So really, like, this sounds like common advice, but it's very easy to forget. You can really actually just write small functions to handle common things, and it will save your life afterwards. And then, yeah, naming things. I mean, I'm guilty of this all the time. I'll name my, data frame DF or something, and then like 20 lines later, I'm like, what was actually in DF? Was it the filtered one or the non-filtered one, or, so. And finally, if you've ever been in government data, PDFs suck. Because someone will put their, data table in a PDF in a pretty report, and they won't have like a CSV file or at least an Excel sheet or anything. And so you have to pull the stuff out. And what'll happen is you copy it, and it'll like the text thing will happen. So you're like, oh, I have characters, I can paste it in, right? And then you paste it into Excel, and it's all like messed up. And you have to like do it by hand, or someone has to do it. And so there are a bunch of stuff. There's PDF tables, which is kind of older, Tabula, which I'm like absolutely in love with, and messy tables. And Tabula especially is like this program where it basically loads up your PDF, and you have this like cool little UI where you drag around your table, and it like pops up basically a screen of your actual data, and you can click download CSV, and it works. It is absolutely magic. I don't know how they do it. It works perfectly. And okay, so just a little bit of advice, and I'm almost done. So using the right types matters. So for example, telephone numbers they're not numbers. They're things that have a certain format. So if you stick them in and if you load them as a really large integer, then you are going to at some point, shoot yourself in the foot. Then this happens a lot with like classification systems and that kind of thing too. And then so parsable things make better, or canonical things make better indices. So if you have numbers, then having like a unique number for every row is better than having like the state name and the county name and the city name for every row. And if there's a universal standard for that, then use that, like if there's a postal code or something. So this I can't stress more enough, because fix data before you need it fixed, right? It's always, by the time data gets to you, you've lost the source of information that could have gotten it fixed. Like you don't know the person who typed in like what kind of weapon they got from the State Department, how much it cost. Like they're not there anymore, and you can't find them. But if this problem was solved back then, like if they had some kind of validation where they said, okay, you can't actually type EA, you have to select it from a dropdown, and it's like each. Or like if they had some value thing that said like there's no way, like this state name actually doesn't make any sense, then none of this would have to have been done. And there's the amount of headache this causes is is pretty major. And so data has a tendency to be used in unanticipated ways, right? So you'll come up with a data set and you'll put it out there, but people will use it in ways that you do not imagine. You can, and so what this tells me is that it's really good to kind of try to put your data out in the least aggregate way possible. So for example, we can look at GDP per capita for a country. So that's like, the GDP of a country and how many people that country has. So those two variables are two separate things, and if you should give those two things separately, then that's much more useful to many more people than if you merge them together, make them one variable, and you lose a lot of information. And yeah, that's kind of it. Yeah.
Do you have any recommendations for data, sort of OCR type
Oh, so that's a big one. There's like a Google, someone from Google made an OCR library that's an open source one, and I forget what it is called, and it works like kind of okay. Tesseract, yes. Okay, yeah, that's what it is. But I found that sadly commercial software works better, and hopefully that'll get fixed over time, but we'll see.
Okay, so Justin's getting set up for Orange. And the other thing we did today, because we had so many speakers, is we did something called like a lunchtime talk. So once Justin finishes up and then we'll take a break. And so for those folks who want to see the data visualization talk, you know, if you already have gotten lunch or you want to see that, we'll take a break for a few minutes. And so folks can come back in. Just that we were in so many different talks. And then we're also going to have a sponsor talk squeezed in as well. So it's going to be almost a continuous, with a short break for lunch. So just to kind of let you know that's going to be coming up. So actually, we should just like ask everyone what they want, and we'll deliver you lunch to your seat, which actually could work better. All right.
Can everyone hear me? All right. Hi there. Can everyone hear? Is this better? Hi, my name is Justin Sun. I'll be talking about Orange Canvas. This is a visual programming environment for data mining. Just a quick overview, why use Orange? I'll be covering a classification tree example, a little bit about the project history, the architecture, some examples of the widgets, and a demo. So why use Orange? Orange is free and open source, and no programming is needed. Although if you really want to write software, Python code, you can. It's a visual programming environment, it's interactive, and it's easy to try new experiment with new visualizations and machine learning algorithms. There are add-ons for bioinformatics, network analysis, such as social network analysis and text processing. This is an example of a complete program in Orange. On the left, you see the file. There's data going into the classification tree and a scatter plot. The classification tree graph will show you the results of running the classification tree algorithm. And finally, we have an attribute statistics link. A little bit about the history. Orange was a university project. Started in 1996 with C++ algorithms. Python was added shortly afterwards, and a GUI based on PyQt was available about 10, 11 years ago. In 2013, Orange Canvas 2.7 was a major redesign. So at the high-level architecture, we have algorithms written in C++ at the bottom. Right above that, we have Python integration, and at the highest level, the visual programming. To install Orange, we can simply go to the website orange.biolab.si. The package comes with everything you will need to install. For example, NumPy, SciPy, PyQt, and other required libraries. This is just a screenshot from the Orange website. Yes, so there are installation packages for both Windows and Mac. This is an example of some of the widgets that are available. On the left, you see the data widget, and we have data going from file to data table, and this is an example of a scheme that you can build. Besides data, you can also look at visualizations, so scatter plots, linear projections, parallel coordinate survey plots, etc. Unsupervised learning. Classification. So we'll go over an example in the demo. And some add-ons for network analysis and text mining. Bioinformatics, if anyone is in that field, you'll recognize some of the names. So let's do a quick demo. So if I were to create a new program, I'll add the data first. So this is the file widget. Double-clicking on the file widget, I can select the data to import. In this case, we're importing the iris data set. There are 150 examples. There are 4 columns and 1 class variable. I'm sure. See if this is better. Is this better? I guess I need to, I'll just hold this then. So we have the file, and I can add a data table. So, I actually need both hands to connect them together. So here we have file and data table connected. If I double click on the data table, you'll see the actual data. So this has 4 attributes. We have sepal length, sepal width, petal length, and petal width, and 3 classes of iris flowers. So we have iris setosa in blue. If I scroll down, you'll see iris versicolor in red and iris virginica in green. The question was, where did the data come from? Orange Canvas comes with a standard set of a standard number of data sets. These are classic data sets that are also available in packages such as R. So I just checked off one of the existing data sets.
How did you make the connection between the file and
Okay, great question. So what I did was I dragged from the right-hand side of file. I clicked and dragged to connect to the left-hand side of data table. So the right-hand side represents the output. The left-hand side is the input to the next widget. So think of them as pipes. So we're connecting data that flows from one place to another. Yes. That's a great question. So the file is built in, but I do have an example of what it looks like. This would be the raw file. It's a tab-separated text file with 3 header rows. So we label each of the attributes, and then there's an indicator to determine if it's continuous or discrete. And then finally, on the 3rd row, we indicate the class variable is the last column. So that's an example of going from file to data table. I can also visualize. So we can also drag and drop items. So here's a scatter plot. Starting at file, I'm going to connect that to the scatter plot. Now notice that you have data flowing from the file to the data table as well as data flowing to the scatter plot. In this case, the data is a copy. So you won't have, for example, part of the data in one widget and part of it in the other widget. We have all of the data in scatter plot. So this is a typical scatter plot. We have sepal width on the x-axis and sepal length on the y-axis. And the color is the class. So remember, we had iris setosa, iris versicolor, and iris virginica as the blue, red, and green. There is an option if you have more attributes. It might be difficult to see how what the interesting two-dimensional plots are. And there's a nice option called VisRank, which will determine the interesting ones for you. So if I run VisRank, it's found that petal length and petal width generate a nice separation between the three classes. And as I go down the list in terms of interestingness, it gets harder and harder to separate the green and the red. So if you start at the top, if you had, for example, maybe 10 or 15 attributes, this would be a very useful tool. So like a cooking show, let's imagine that we've baked this, and now 30 minutes later, I have a final product. So in addition to the scatter plot, I have attribute statistics. So you can see the mean, median, min-max, and 25th and 75th percentiles. And here I've added the classification tree that's found under the Classify tab. So in this case, we're taking the default values and we're generating a classification tree based on the iris data. And this is the result. In a classification tree, we're taking all of the example data and we're determining rules that can separate the classes. So in this example, if I hover over this, it says, if petal width is less than 0.8, then predict iris setosa. And similarly, if petal width is greater than 0.8, then predict one of the other two colors. One of the interactive features is the ability to connect selections from one widget to another. And I just wanted to give a quick example. So if I select for example, iris setosa, all of the iris setosa examples show up in the scatter plot on the right. And if I select this item, then we see the other two selected. So this is just an overview of some of the things that you can do. I have one other example I wanted to show you. This is to test and evaluate different learners. So in this scheme, we're taking the same iris data set. We're taking a sample of the data. If I double click on data sample, we have 2/3 of the data are getting selected. We also run the classification tree algorithm, and we generate the graph. In addition to running the algorithm, I'm also using test learners, which will take the input from the output from the two different classification methods and evaluate those methods. So here we have the data coming into the test learners. So if I double click, we are seeing the comparison of naive Bayes and the classification tree, and we have certain performance scores, including the classification accuracy, sensitivity, specificity, and area under the curve. You can also select some of these others, which are not all selected. Now, one of the common things that you might do is you'll want to try many different examples and remember what you've done. There's a feature called report, which will help you remember the different activities. So if I click report, this will add in, for example, that I've opened the file, that we've run a sample, and we have perhaps a classification tree graph that we want to save in the report. And then you can print out the report or you can save it. You can use it for reference later. Okay, finally, yes, question? So the naive Bayes is using, so test learners takes all of the data in, and we have options for the evaluation. We have, in this case, chosen cross-validation with 10 folds. What that means is we will take 90% of the data. So we divide the data set, the entire data set, into 10 chunks. And in each of 10 runs, we will withhold one of the folds. So 10% is held out as a test, 90% is used for training. We'll repeat that 10 times and take the average. So that's how the numbers are calculated. You can also use leave one out. And this is actually recalculating and redoing the evaluation. You can do random sampling and test on training data, which is not recommended. Okay, another question? The data is file-based. The question was, can it be live data or database data? In the next version of Orange 3, there will be support for databases. In the current version, there's an experimental widget that you can use to select data from a table. So I just wanted to wrap up with those who actually want to code. I have a very quick example. You can actually write import orange in Python, and in this case, we're just outputting the summary stats similar to the attribute statistics widget. Okay, and to conclude, I just want to leave you with some resources. The best resource is probably the Orange website itself. There's some tutorials, interactive network analysis paper, and a white paper on scripting. Thank you very much. Are there any more questions? I'll be around afterwards.
Yeah, and as mentioned, we're going to be having a really condensed schedule, just and so one change we're going to have is Pete, one of our sponsors of the event, who are helping to support the video production and everything. I have a couple lightning talks, and so we're going to have Pete give his lightning talk now, and then the biotech one we're going to have Pete, the visualization, and then Will Sutton's biotech is going to be right at 1 o'clock, just his lightning talk as well. So the lightning talks, we have more flexibility to move. When you look at the schedule and you see like the 45-minute block of there's glue and then there's Nifty, those are going to still be in the same block. It's just the lightning talks we're going to have a little bit of kind of changing. So I will hand it over to you. Like to use the mic here or the
1, 2, 3.
You are all set. Okay.
Hello, can everybody hear me? All right. All right, I'm Pete Martin, VP of Engineering at Pixability, and I'm here to talk to you guys about our technology, data science, YouTube, and media disruption. So what does it all mean? First of all, YouTube's huge, right? It's really big. Some of the numbers that I like to quote here, it's actually world's second largest search engine. It gets over 1 billion unique visitors per month. 17% of internet's traffic actually flows through YouTube, believe it or not. You know, some other numbers here, quarter of YouTube's traffic is on mobile. 100 hours of YouTube videos are uploaded every minute. And one of my favorites, YouTube produces in 60 days more content than traditional television has produced over 60 years. So why do we really love YouTube? And if you say because it's the cat videos, I'll ask you to leave. I'm sorry. It's big data, right? So there are order of tens of millions of channels, hundreds of millions of videos, everything we put in a list. And you can engage with everything, right? Comments, subscriptions, likes, dislikes. On top of that, we have other massive social platforms connected to YouTube, Facebook, Twitter. And let's not forget the entire ecosystem is changing, it's moving. Every single metric is changing over time, right? So another comparison to traditional television, Nielsen, a TV rating company, estimates that Emmy Awards show gathers around 15 million viewers. And you can see on the left side there are some other shows, NCIS, America's Got Talent, 10 million, 60 Minutes, 7 million. These are popular shows on television. In contrast, anybody know PewDiePie on YouTube? Raise your hand. All right, bros. All right, PewDiePie is a PC game commenter. He plays games, he comments on them as he does it. He's got 30 million subscribers. These are not even viewers yet, these are just subscribers. He regularly puts up videos that get 2 to 5 million videos each, and he publishes videos every day. So that gives you an idea of where we are with YouTube compared to traditional television. There are some other creators here, very popular. Some of them are comedians, some of them are gamers. One there, Michelle Phan, with 7 million subscribers, has a channel where she essentially puts up tutorials on how to apply makeup. Very popular. She's not actually selling anything, but you can tell that it's a great opportunity for brands because she's actually using those products, right? So brands, marketers, have a number of challenges. One of them is, what kind of content should I be producing, right? Should I be aiming to produce viral videos? Should I be trying to do tutorials? What about discussions with experts? Maybe just product reviews, right? It differs by a different vertical. The other question they might ask is, how do I promote it effectively? Where should I advertise to drive audience towards my channel? Thirdly, how do I make it discoverable? Search results, right? It's a classic search engine optimization problem. And finally, assuming that I get the right audience to my channel, how do I engage them such that they view my videos to the end, they subscribe to my channels, they maybe go to my website, maybe they go to my e-commerce site and purchase my products. So Pixability has built technology that can solve and answer these questions. We have sort of 3 distinct frameworks in our platform. As you can see on the right side, we're using a variety of storage systems. We found that no single storage or no single solution can really answer all your questions, and it really varies by function. So we use Elasticsearch quite heavily. It's great for full text searches, for textual information. We leverage a number of other ones, obviously, for different purposes. So our data retrieval framework, analytics, is able to detect when we are missing data or have stale data. It can send commands to the harvesting framework to essentially harvest all this information from these sites, primarily YouTube, of course, but we crawl other ones as well. And then finally, the data processing framework is able to make decisions and optimizations for things like advertising and make actual push actions to things like AdWords for video, those types of sites. Needless to say, all this stuff is built in the cloud with fully scalable and can be all done in parallel. So as far as our data science, first of all, we love Python. We develop a number of proprietary algorithms. There's obviously patents pending. We also leverage pandas and NumPy for a lot of our stuff. Our algorithms range from content and ad classification, trend detection, and not only per video, what are some of the viral videos that are out there, but also kind of trends along industrial lines and vertical topics. Things like abnormality detection in ad serving, right? When something changes and you're not quite sure what it was. We have algorithms for ad placement recommendations for channels as well as videos, in-flight app optimizations, A/B testing, and classic analytics. And I should mention that just this past week, we were the recipient of the Mass TLC 2014 Technology Award in Big Data. So that was a big deal for us. So another, you might ask yourself, like, what can we find out from all this technology? So when we approached a consumer packaged goods company, and we talked to them about advertising to young males, they told us, after they've done a lot of research on their end, is that they think that young males watch sports, lifestyle, technology and cars, and health and fitness. And this is where they wanted to spend, 7 figures on advertising on YouTube. We did our research, and we found something slightly different. Apparently, young males spend majority of their time on music, comedy, and video games, right? And of course, there is these other sectors as well, but they're not dominating the audience. So we essentially helped this company avoid a $1 million mistake in advertising and help them achieve better results. So another company we worked with was asking us, when and where do women watch makeup tutorials? And the hint there was not on TV prime time. So we have done some analysis based on YouTube search results. And we found that when somebody searches for a particular brand of cosmetics on YouTube, this line is fairly flat throughout the day. The x-axis here is our time of day. However, when we looked at tutorials for makeup, we found a completely different picture. And as you can see, the two big spikes there are like 7 a.m. and 10 a.m. Anybody want to guess why we have those two spikes there? Why they're 3 hours apart? That's right, East Coast and West Coast. We also have 2 more spikes in the evening. Anybody dare to guess where the videos are being watched from? It's from the bathroom with the phone, right? This is where this kind of content can be consumed, right? This is definitely not in front of your television in the living room. Yeah, some other tools and visualizations that can be quite powerful, even though fairly simple. So Sephora's channel gets about 30 million views. If you look at all top beauty brand channels, there's about 1 billion views. But how big is really this market, right? When you look at all of the top beauty brand mentions that are not done by those brands, but rather by the independent vloggers and creators, we're looking at a 13 billion views market, and even bigger market of beauty in general is close to 20 billion. So when you come to somebody like Sephora, one of these top brands, you can tell, look, you really don't have a lot of voice in this market. Let us help you optimize and get better results. So some of the results that our customers have seen with our technology, we've been able to drive organic traffic towards channels 6x. Similarly, click-through rates are often between 5 to 10x better than just straight ad campaigns. And some of our customers have really found it that YouTube became a #1 and cheapest acquisition method for customers. So cost per acquisition is vastly reduced with our software as well. So this is a visualization showing our general customer trend sentiment. Yeah, we have a bunch of positions open. We're right outside here on a table right outside the door. If you guys like to come by and say hi, I'd be happy to. Also have another talk, I think, at 1 o'clock upstairs. So any questions? All right, thanks very much.
Which type are you looking for?
Best way to connect?
What's your output?
RGB would be better. RGB, I mean.
Okay, so our next speaker is, how's your first name?
Patrick.
Patrick Lundblad. He is a data visualization expert, and he's going to be walking through exploring data viz. He's I'll let you kind of do the introductions. But how are everyone doing? Well with lunch and sodas and all that? All right, cool.
So switch over to.
Sometimes So which one did you choose?
VJ. Yeah, perfect. So thank you. Can everyone hear me, or should I adjust the mic slightly? Slightly. That's better. So my name is Patrick Lundblad, not Pratik or something like that was in the schedule, but yeah. I just arrived from Sweden yesterday evening, so I'm slightly tired, if you don't notice that. I have a PhD in visualization. So before I actually start, I want to know who you are, because this is my second time to Boston. How many people of you are academics? Couple. How many of you are in incubators? Small startups? How many of you are in larger companies? What are the rest? So I've actually been in academics for 5 years doing my PhD, mostly around applied research, looking at how you can take visualization, apply it to real-life data, and make use of it. Together with a professor and some other PhD students, I created a spin-off company. We did statistics visualization for IMF, Eurostat, European Region, European Space Agency, a couple of other organizations. And then we were acquired, decided that, yeah, let's focus even more on visualization and work with another company around it. So now I'm a part of a bigger company and just learning how that life is. So I'm actually going to talk to you about some concepts. I know you had some introduction to data visualization yesterday, so I'm not going to dig too deep into the basics, but I want to focus on 4 areas that I really like. But before that, how many of you have seen this one before? Most of you. I know Tufty is here, talks sometimes to you. This is Minard, 869. This is early data visualization, not even data. This is about Napoleon having his army over here with 400,000 soldiers, wanting to reach Moscow with 100,000 soldiers, failing to do this, and then retreating with his army back, arriving back to Lithuania with 4,000 soldiers. So you can read the entire book about this. There's actually a new one out recently. But this is all about comparing 400,000 soldiers to 4,000 soldiers. It's about 2 data sets of his army marching towards Moscow and back from Moscow. It's about the temperature, minus 30, some French scale, which is around minus 30 degrees, 40 Fahrenheit, and so on. So really already back in 869, we knew how to visualize data. Going forward from then, we actually know why we can visualize data. So I'm going to show you a couple of numbers. And I want you to raise your hand as soon as you see number 3 among these numbers. Almost everyone is on the game. So if I do this again, can you raise your hand when you see number 3? And that was quite a bit easier. Do you know why? It's colored. So we have something called visual perception. We like to divide this into 3 stages. The first, second, and the third stage. The first stage is all about neurons. We can detect edges, color, texture, movements. The second part is more of pattern, contours, motion. And then the third part here is about us actually thinking about and seeing and trying to interpret data. So the first stage is really great because we have what's called pre-attentive processing. If we look at something and it stands out to you in less than 250 milliseconds, it's pre-attentive. Your eyes are immediately focused to the things that stands out to you. May it be color, may it be shape, may it be orientation, size, or even clusters. Your eyes are drawn to that area immediately and you start analyzing. So all of these things been documented, 1980s, 1990s. You can read about them and how to use them. You got pattern perception. This is the second stage. You can immediately look at this scatter plot here and see the clusters, how they are divided. You can also look at this line chart here and see there's a missing area in there. But your mind doesn't care about that. You're automatically creating a line that connects to this one here. So you're looking for contours, patterns, motions, and so on. And then got the third stage, which is when you actually start looking at these scatter plots individually, loading one of them into a chunk in your memory, and then comparing that chunk with another chunk to see what's the difference between them. But this is purely academic. I actually like talking about how you can use it. So this is one of the most popular car renting places in England. This is Lynx Cars. She was actually at the Dragon Den, and she actually has 100,000 customers. But imagine going to this website, and if you actually look at the real one, it has flash animations all over it. There's this person up here dancing and walking around and colors and all those. So what are you looking at? You have no idea. But let's do it in a reality. I mean, if you have a table, this is Excel, you want to style it, you want to make it look beautiful. But the color up here doesn't stand out. It's hard to read the numbers, they're uneven and so on. If you use the perception rules that I just told you, you immediately see that Macho Man Randy Savage stands out as being something important because red stands out against the background. The second part here, I actually don't need to repeat all these names here because automatically you're creating groupings here because there's space in between here. So you know that these three names goes to Jobber, the unknown. And then the third phase, you're looking at the numbers. I'm using a common denomination of thousands, and I'm using ratio. You're comparing them to each other. So that's just how using visual perception rules and making something harder to analyze to making it easier to analyze. Because I know exactly how a person looks at this chart, table, and how they analyze it. Another thing that's really interesting is color. So 8th grade science, biology, I guess you all know how an eye works. You have light coming in, you have cones, you have rods. Interesting enough, we actually have 125 million rods in average. We only have 7 million cones. So we're actually perceiving hue much more than we're perceiving color. And as an example, let's do a quiz. This is the birth dates in a country by month and day. And the darker is, the more common a person is born on that date. And the lighter, the less common. Can you identify the country? Everyone says Sweden. That's the context that I'm from Sweden. So it's not Sweden, actually. It's the US. And why? What happens 4th of July? Independence Day. So you are all out celebrating. You don't want to have a planned birth on the 4th of July, meaning that you schedule that planned birth for 2 days later or the day before. People are still born on 4th of July, and congratulations to them, but you don't plan a baby to be born on that day. Same thing, Thanksgiving. You don't want to have children during Thanksgiving or Christmas. This probably is most countries here, but 4th of July is the one thing that stands out to me that I can analyze this data set with. When it comes to color, we divide the cones into the red hue, the green hue, the blue hue. And I'm not saying that you're seeing blue less, just that because you have less of these, because we probably inside our mind have a blue color magnifier that magnifies the blue color. What's interesting is if you look at the fovea, if you are a person who have no colorblind deficiency, this is what it looks like. The red receptors, the green receptors, the blue receptors. If you're colorblind instead, you have this instead. You're not actually seeing the difference between green and red. You're still perceiving red, but it goes to the green channel. So, quick and easy test. What's on the left side? Which number? 16. Everyone can see number 16. What's in the middle? 7. Most people can see number 7. Some people can't see anything. What's on the right side? 3. Did anyone say 3? So if you see 3, you have a slight deficiency towards color blindness. So, I mean, this is really a great way of knowing what people can see or not. And I really like to talk about color, but I don't have all the time here. So I'll just recommend colorbrewer2.org. You can go in there, you can specify what kind of color scale you like. You want to use hue, you want to use divergent, you want to use qualitative colors. And it will actually tell you which ones are colorblind friendly, LCD monitor friendly, VGA projector friendly, print friendly, and so on. And as long as I've been doing visualizations, I've always been complimented about my charts looking so good. This is the secret, because I have good looking color scales. So, how can you use data? How can you use colors? Quite often, people put this in, and this is the rainbow syndrome. A chart is boring, let's add color to it. You perceptually look at this red bar being higher than this blue bar because it's more intense to you. It actually stands out. If you scale away the color, you can immediately see which bar is higher, which bar is lower. If you use a sequential one, you can see what's higher, what's not as important. Diverging, this is often temperature scales above, below a certain value. You can see something is above or below. Or, my favorite, the Skittles. I actually have product sales here, and I have categorized them by what category they are. So this is just like Skittles. I take up a blue Skittle. I know what it's going to taste like. It's going to taste exactly the same as every other blue Skittles in the package. So you can see here, best-selling products, menswear, then female, and baby wear is more in the middle. So same you saw in the presentation, 2 presentations ago. What cluster do you belong to? Easy to see. And this isn't really news. This is 1980s research and forward. So you can find these books and other books that have really great topics around this. But let's talk about some of the more modern concepts, that of animation. If you look at this picture here, this is a tapestry all kind of on my grandmother's place. Is there anything in this picture that stands out to you? Someone actually screamed, best reaction this week. So we are really good. So this is the first part. We are really good at seeing transitions, animation, and so on. They stand out to us. But how many haven't seen this on the left side with Hans Rosling telling you, look at China here, look at the population, it's actually growing until Mao Zedong comes in and people start dying. That's great because he's up there, he's telling you what to watch. But the animation here mainly tells you the overall movement. If I ask you to follow this blue bubble here, can you do it for me? Have you lost it? You lost it, because this is exactly the same thing birds use in nature. They fly together in a flock, constantly moving around each other because they need to be safe. If a predator is outside there looking at one of these birds, it makes a U-turn, it goes behind another bird, it just goes in a direction you didn't expect, you lose it. So if you have bad results anytime or anything, just animate it because no one will ever be able to find you among everyone else. Unless you go across the stream, because you need to follow that movement. But animation can still be good. I like animations when it comes to transitions. I can see how a bubble changes as I do selections. So instead of just having bubbles disappearing, appearing, I can tell you how does a bubble move from one state to another. And it's really not hard implementing this. Already back in 1930s, Disney were doing transitions. So this is, for example, slow in, slow out. This is transition I want to use when I have an axis changing scale. So in the beginning, I'm changing the axis scale slowly, and then I'm speeding up until I reach the middle. Then I decelerate and go slowly in the end. That way I get a much smoother transition than just having a linear transition all the way through. So good paper back from the 1930s around how to do animation. Focus and context. This is another deep dive. You see I'm all over the place when it comes to visualization right now. You've all seen this one before. Moore's Law or so. 128 megabytes, 128 gigabytes, just 9 years in between. So we all know we're getting more and more data. But my question to you is, in this time between 2005 and 2014, by how many times has your screen resolution increased? Has it increased by 1 million or not? It's increased maybe by 4 to 10 times at the most. And it might actually even have decreased because you're now sitting on a smartphone that is less resolution than you had before. But still, we have larger data sets. We want to visualize it, but we don't have the screen resolution for it. Hence, we're, for example, using tree maps. It is 100,000 data points to visualize all that data together on this small screen. Or you can use one of the contexts that come from information visualization. If you ever take a class with Ben Snyderman or someone, he's going to have you for 1 hour stand up and repeat overview first, zoom and filter, details on demand, because that's how we work in information visualization. Visual analytics, kind of different, but still same. Analyze first, show the important, zoom, filter and analyze further, details on demand. What this tells us is that if we can show the user an overview of the data, then they can dig down into details. And there are many ways of doing this. For example, you can use trellising, small multiples, and so on. So this is a data set with 6 variables. Instead of having a scatter plot and comparing them one at a time, I can do a trellising and see the overview of the data. What are all the possible combinations? Such as you had the iris data set. You can do the same thing here. You can see immediately which ones stands out against each other visually. Or you can do fisheye lens. So this is a billboard up here. I have a small part of the billboard I'm focusing on. Let's say I take 2 pencils. I put the billboard here. I can actually then focus on it and see the context. Let's see, I'll skip this one. So what it actually ends up with is, for example, if you have a bar chart, you have a few bars that you want to focus on. You can put a focus in here in the middle, a certain amount of bars. You have the details about who they are, what numbers they have, and exact values that you can measure. But you can still have a context on the side with those other 100s of bars that wouldn't fit on a screen normally. And if you add interactivity to it, it's easy to scroll through a data set of thousands of bars and always see where are those bars related to each other. So just a simple fisheye technique applied to a bar chart. Or overview and details. This is 10,000 zip codes of Sweden. If I would render every zip code on this map here, some of them would be smaller than 1 pixel, or they would overlap each other if I had the borders and so on. So in here on the left side, I'm just using a heat map. So for each pixel, I'm looking at what's the value in below there, the average value. And then I have a details view here telling me exactly the zip codes. And even down here in the city, I can zoom in and see to a street level what are the values, but still knowing where I am. Third area, responsive visualizations. So we're all used to watching a visualization on a projector, 1024, 1280, or something like that. What happens when you take a visualization to an Android device? This is the amount of devices available for Android. And this is how many people have a certain device. So if I'm going to design a visualization and it's going to be able to use on a mobile, I need to know what mobile are they using it on. So I need to maybe program and adapt to all of these ones. Or I can do another thing. I can look at the screen resolution for all these mobiles. So each area here is a certain resolution. And this tells me that if I'm doing visualizations, I can't say they're going to be 400 by 400 pixels, because I have no idea if they're going to be able to display or not on certain devices. Simple. So what we do is we take something from the web called responsive design. How often have you taken up your mobile, iPad, Android tablet, or so on, and not been able to see a newspaper? Because they're using a responsive design, meaning that they're adapting their area that they have so that it fits actually on the screen. So for example, a normal website, really large, looks like this on a screen resolution, PC. It scales down to be a different area on small devices. They're probably not getting as much detail in the end. And you can do the same things with visualizations. This is a dashboard with a couple of visualizations. So if I'm looking at this on a smaller device, I can simply use responsive design and say I want to look at one chart at a time. But I'll also show you something I think is pretty cool that we're working on, which is responsive visualizations. Meaning that it's not only the design and layout of the charts that are responsive, but the visualizations themselves that are responsive also. So I have created before a bar chart. Let's add this. So a bar chart normally is quite simple. I'm seeing the height of the bars. I'm seeing the days here. I have an axis here, 0 to 6. What happens if I start scaling? I actually have the exact space for all these bars, luckily. But what happens if I start scaling it down? So when I don't have as much space, we're of course making all the charts smaller, pixels smaller and so on, or the font size smaller. But when I reach a certain size, I introduce a mini chart down here. So I can still see all these charts up here, but I now have a scroll bar, and on that scroll bar I can immediately see where everything is available. So I can start scrolling around. If I make it even smaller, you can see then that I take away the dimension the labels here, telling you exactly what it is, and I'm then starting to just narrow it down so it always fits. So still trying to show as good visualization as possible, but having it adapt and be flexible to screen resolution. That's quite simple. You just put up a layout and you just do the responsive design within the charts. Or if you have a sheet with many charts on it, each of these charts are then responsive, so that they show more or less depending on the screen size that they are assigned. And if you go into mobile mode, you're then viewing them one chart at a time. Last part, interaction. So everyone knows what it is called QWERTY. And anyone knows why they are placed where they are? Type. So this is a typewriter where you have these up here hitting the paper. And you don't want two of them next to each other hitting the paper at the same time, because they could actually jam together. So you want to spread out the characters so that two characters used together are not next to each other up here, but still pretty close to each other. So this is from the 1900, and it's based on the English alphabet. And being a Swede with a Swedish keyboard, first of all, I've never had my Swedish keyboard jam upon me. I can tell you that. Second of all, I'm forced to use a keyboard that's based on the English language. And I know you have small differences between them, like color and color. But for anyone else who's not an English speaking, QWERTY doesn't make sense for us. It's much easier for me to write in English than it is on Swedish as it goes to the speed. So what we have instead is Siri or the Google one or the, I can't remember all the names. People talk to a computer, and computer does, hopefully, what it's supposed to do. I still can't use Siri because she doesn't understand me. Or you have the mouse, as in you can actually interact with a mouse. You have this hand here holding this mouse, and you have a cursor moving on the screen. Good innovation. What's even better is touch interaction. So I actually had a problem with my mother calling me last year, once per week, asking a computer problem. How do I do this in Windows? How does this work? If I click here, what happens? Control A, what do you mean? So this last Christmas, I bought her an iPad. She still calls me once per week, asking, what's the latest app you've downloaded? Can't we play together on one of these games, Word Feud, Quiz, or something like that? But she, and I mean even a 5-year-old child, you've seen those YouTube videos, can immediately use a touch interface. And I actually don't know if we have sound in here that I can connect to my computer or not. Otherwise, I'll just speak to it. So we'll see if it works or not.
Are you able to find an audio jack?
We'll see, otherwise I'll talk to it as it is. So we've been working, me before when I was in university, a new way of visualizing data and interacting with data.
Powerful interactive visualization system. It enables museum and science center visitors to interact and explore real subjects, scanned using CT and MRI technology. Inside Explorer is based on powerful interactive visualization hardware and real-time volume rendering software that unlocks the power of discovery for museum visitors and museum curators alike. Inside Explorer is today used at museums and science centers around the world, allowing visitors to explore everything from mummies to Martian meteorites. It is easy to use and requires no training or special knowledge. By using intuitive multi-touch gestures alone, the users can investigate complex subjects that have been scanned using CT and MRI scanners. Visitors can peel away layers, rotate, zoom, and cut through subjects and reveal hidden interior details. Anything that can be scanned can be visualized, explored, and used as the basis for an interactive, authentic user experience.
So that's kind of something that you hopefully will see at the museums. They have some at British Museum now and testing at other places. They're also doing virtual autopsies using this, which is, I would say, much better. But it's still something that everyone can engage in. It's much more a feeling of moving something around that's 3D, using your fingers on a touch device, rather than a computer, holding down Control, holding down Alt, depending on if you're scrolling, rotating, or zooming, and so on. So that was kind of me in a 30-minute nutshell when it comes to visualizations. Any questions? Yeah, apparently, yes. I mean, I can give a copy to the organizers, and then how the organizers get it out, that is up to them. Yeah. So if there's nothing else, back to lunch for you. Oh, yeah.
So some of these things you showed, are more interactive on the web, but if you have to give PowerPoint slides like printouts, what's some of the best practices?
Some of the best practices when it comes to PowerPoint printouts are back to 19th century. I mean, the way Minard described data using just a canvas or paper and his pen and nothing interactive, he actually had to look through all of the parts as in how can he take 4 different data sets, combine them together. So let's actually go back to so he's actually cheating a lot. The background map here is not a good representation of the real background. You would not want to navigate